Good morning to all. Welcome to the third day of Faculty Development Program on Miniaturized Machines and Devices, organized by Government Polytechnic College, Perinthalmanna, in collaboration with SITR. The illiterate of the 21st century will not be those who cannot read and write, but those who cannot learn, unlearn, and relearn. And this process of learn, unlearn, relearn is important not only for personal development but also crucial for national building. Artificial intelligence, contactless machines, and automation will change the world drastically into the next decade or so. Learning is a continuous process to keep pace with the rapidly changing world and technology. Today, we have 3 sessions. The first session is about nanospectroscopy using tip-enhanced Raman spectroscopy. Dr. Shantanu Kumar Parida is with us to share his knowledge. I welcome Dr. Shantanu Kumar Parida to the session. Dr. Shantanu Kumar Parida is a postdoctoral research fellow, Weizmann Institute of Science, Israel. He has received PhD from Homi Bhabha National Institute, Indira Gandhi Center for Atomic Research, Kalpakkam, Tamil Nadu, India. He has received many awards and honors. He was outstanding doctoral student. He has received outstanding doctoral student award from HBNI, Bark, Mumbai, India. We are truly honored to have you here for our FDP. Welcome to Mr. Shantanu Kumar Parida. Over to you, sir.
Thank you very much. I thank the organizing committee for giving me this opportunity to share my few works which I done during my PhD works, and I will be talking about the nanospectroscopy using deep enhanced Raman spectroscopy.
Sir, you can share your screen actually.
Yeah. Now, can you see?
It's visible, sir.
Yeah, sure. So today I am going to talk about the nanospectroscopy using the tip enhanced Raman spectroscopy. The work is mostly done in my PhD career at Indira Gandhi Center for Atomic Research. So this is the outline of my talk. So starting, I will be introducing what is spectroscopy, why we should do the spectroscopy for the material characterization and all. Then I will be talking about the Raman spectroscopy, which is of course developed by the Dr. C.V. Raman, which is a first Indian Nobel laureate in physics from India. By his name, the Raman spectroscopy is named, and it has a various application from starting from physical science to chemical science to biological science. It has a wide range of application. So I will be introducing the Raman spectroscopy, and by using the Raman spectroscopy in material science, what we can do, and different things which we can extract, with the physical properties which we can extract from the material using the Raman spectroscopy, that I will introduce. Then I will be moving to the diffraction limit. Regarding the diffraction limit, the subdifraction limit, Dr. A.K. Shivadasan in the first session, he has talked about a lot, and how to confine light in the subdifraction limit and all. So I will be just give a glimpse of that, and I will not be discussing much. So after giving a glimpse, then I will be talking about the coupling of atomic force microscopy and Raman spectroscopy. how using the atomic force microscopy we can confine the light and use Raman spectroscopy to break the diffraction limit. I will be talking about that. Before that also I will be introducing the atomic force microscopy technical things, how it works and what are the different modes it works and all. Then at last I will be talking about the nanospectroscopy technique, that is the tip enhanced Raman spectroscopy, and few examples of, in the past what people have done and how they have achieved different things and all, how they have characterized the material to get different physical properties. Then I will be showing also one of my result, which is the single gallium nitride nanowire device basically. So I have imaged the spectroscopical image of the single nanowire, which is of course the first time we have achieved a single nanowire, which is the diameter is around 200 nanometer, which is far below the diffraction limit. So with this, we'll move to our topic. So generally we talk about the spectroscopy, and in material science spectroscopy is used in various applications. So what is spectroscopy? Spectroscopy is it's basically a typically light matter interaction. What happens? We gives the electromagnetic wave, the electromagnetic radiation to the material, and with the help of this radiation, it interacts with the matter. So it is basically a light matter interaction by which we can determine the physical and electronic structure of the material. So we use the light matter interaction to determine the physical and electronic properties and the electronic structure, and which is of course the is a function of wavelength or frequency. Since we give the electromagnetic radiation, so what we get is a function of wavelength or frequency. So according to the different probes we use from the, as we know, the electromagnetic waves range from the gamma ray to cosmic ray and all. So according to their energy and or frequency, they have categorized in different categories. So if you use X-ray absorption or UV visible spectroscopy, these two techniques generally probe the change in electronic structures in the material. So what we can, by using this X-ray absorption or UV visible spectroscopy, generally we can find the band gap, since it deals with the electronic structures. So we can find the band gap of a material. We can see the electronic structure, electronic density of states we can see. So these are the different things we can probe in a material by using this technique. Next, we can move to the IR or Raman spectroscopy, which is generally use the electromagnetic wave in the visible region. What it does is these two techniques basically probes the vibrational states. So as we know, there are in the material there are different electronic states, vibrational states, and rotational states. So these two spectroscopic techniques, they are very powerful techniques to probe the vibrational states. As we know, in a material, all the atoms and molecules, they are not stable. Every time they will be vibrating with respect to their mean position with the certain vibrational frequency. So what we do, we probe these vibrational states using the Raman or IR spectroscopy, and from that vibrational states we analyze that, and we can find out which material is this, and in which state it is this, which phase, basically if it's a cubic phase of material or tetragonal phase of material or hexagonal phase of material, that we can see. And basically using the IR spectroscopy also we can see the atomic level, which is the absorption, hydrogen absorbed in the material or helium is absorbed in the material. So these kind of things we can do using these two spectroscopy techniques. Similarly, there is a microwave spectroscopy also, which uses the microwave range of the electromagnetic radiation. And using the microwave spectroscopy, we can see the rotational states. Generally, it probes the rotational state in a atom or molecule. So by using the microwave spectroscopy in the material, we can probe the rotational states. So this is the typical electromagnetic range, and this visible range actually we use mostly the visible radiation in the Raman or IR spectroscopy. So now mostly I will be talking only about the Raman spectroscopy. Other spectroscopy techniques like it will be a vast to talk. So I'll be restricting myself to only Raman spectroscopy, and later I'll be talking how using Raman spectroscopy we can do several things, and coupling later on the steep enhanced Raman spectroscopy and all. So Raman spectroscopy is basically inelastic scattering of light. So what is inelastic scattering? We shine light in a material. So what happens? It absorbs some light, it reflects, and so many phenomena happens in this. So what happens if we radiate a light and it comes with a frequency or energy which is higher or lower than the radiation frequency, then it is called as a inelastic scattering. So in most of the scattered light comes with the same frequency. So they are called as Rayleigh scattering. So other very few in like in 1 in 10 to the power 15 comes as a.
Sir, excuse me, sir.
Yeah.
Sorry, you just use that mouse pointer while explaining. Then
Yeah,
we
yeah.
can. Thank you, thank you.
Yeah, sure. So only few comes with the higher energy or lower energy. So what happens when we give light to the matter? It absorbs few energy from the matter. It absorbs in form of phonon. Phonon, we know it is the vibration of collective vibration of atoms in the matter. So if it comes with a little higher energy, then it is called as a anti-Stokes line. And if it's come with a lesser energy, by giving some energy to the material in the form of phonon, then it is called as a Stokes line. So this is the basically the energy diagram, where you can see this is the Rayleigh scattering. The emitting photon has the same energy as of the incident photon. However, in the case of Stokes, it comes with a lesser energy, and in case of the anti-Stokes, the radiant energy and the scattered energy is different. So it comes with a higher energy. So that is called as a anti-Stokes. So this is the selection rule which governs the Raman spectroscopy. Where I am not going detail into the mathematical expression, but if we give a electromagnetic radiation to the matter, so the induced dipole moment, that is the P, is given by this expression. So the second expression, you can see it contains two terms. The first term is the contains the frequency, which is nu 0 plus nu m. This is, comes with a little higher energy, that is called as anti-Stokes line, and which is comes with the lesser energy, that is the nu 0 minus nu m. It is the Stokes line. However, you can see there is a term that is del alpha by del q. So this is the change in polarizability in the system. So if this term is non-zero, then only we can get this Stokes line and anti-Stokes line. Otherwise, you cannot get. So this is the basic things. The thing is that this is the selection rule. So if there is a change in polarizability in the system, then only we can get the Raman spectra, that is the inelastic scattering in the material. Then only we can probe the system and get the different properties of the world. Otherwise, if the change in polarizability in the system is zero, then we cannot perform the Raman spectroscopy in the system. That's why I just want to point one thing. In metal, generally, Most of the metal we cannot probe with the Raman spectroscopy. This is because the change in polarizability tends to 0. So that is the one of the reason. There are some other aspects also. So basically, in most of the metals, the change in polarizability is 0, and we cannot probe the metallic states by using the Raman spectroscopy. So yeah, as I discussed, this is the Stoke line. This is the incident photon. So what happens? It gives some energy. That is the Q. That is the in form of the phonon to the system, and gives comes with the rest of the energy. So this line is called as Stoke line. Similarly, in the anti-Stoke, what happens? It receives some energy from the material in the form of phonon, and comes with the modified energy. So here in the Stoke line, you can we can call as it is like a creation of phonon. Since it gives energy to the system in the form of phonon, we can tell it as a creation of phonon in the system. Similarly, in case of the anti-Stoke, since it's received the energy in the form of phonon, and that phonon annihilates, so we can call the anti-Stoke line as annihilation of one phonon in the system. And this is the typical phonon structure, acoustic phonon and optic phonon in material. I don't want to go to detail, but only thing I just want to point out that whatever we probe using the Raman spectroscopy, that is the optical phonons, and it is near to the zone boundary. These 2 points I just want to emphasize. Other things you have to go to details to see why it is only at the zone center and why only optical things and all. Just at this point of time, I just want to emphasize these 2 points. We probe at the zone center, and we probe only the optical phonons, not the acoustic phonons, using the Raman spectroscopy. But there are several contradiction also, and sometimes the selection rule breaks, and we can see also the acoustic phonon. That is something different cases and all. So with this, now this is the typical Raman spectrometer, which is the so basically it contains a microscope, so which uses used to focus the sample, and other things is it consists of a laser which gives the electromagnetic radiation. So what happens here at the X-ray stage, we keep our sample and focus using the microscope, the optical microscope generally we use. So what happens when we give the laser, it comes with the different lenses and all, just to focus different mirrors and all. And here like this, it comes to the material. It shines laser on the material. Then at the then the electromagnetic radiation, that is the incident laser, scattered back. So mostly we use the back scattering. So back scattering means at the 180-degree scattering itself, it scatters back, and the scattered photon goes like this, and through a grating it dispersed to the detector, and we uh, detect the photons which are inelastically scattered using the CCD. One more thing I just want to mention. Here there is a Rayleigh filter. A Rayleigh filter, what it do, while the scattered photon goes here, it blocks the photons which is having the same energy as of the incident photon. So as I mentioned in the earlier, the most of the photons comes with the same energy, that is the Rayleigh scattering. So we use a Rayleigh filter to cut all the lines which are having the same energy, and all other things, other scatter light passes through the grating, and it comes to the detector, and we detect the lines, and from that line we analyze the things and get the Raman spectra. So using Raman spectroscopy, what are the different informations we can get? So what we can do, we can do the compositional analysis. So this is the typical Raman spectra. So with the different material and all, this characteristic spectra will change. So if let's say it's the material of gallium nitride or silicon or germanium. So if germanium is giving the peak at 450, then silicon will be giving the characteristics peak at 520. So by analyzing this spectra, we can tell that which material is this. So that is the silicon or germanium or MOS2 or gallium nitride or anything. So this is the one of the most powerful things to do with Raman. So that's why this Raman is nowadays considered as a basic characterization tools. So why basic means just you put your material, you made a material, so you want to see this is in which phase it has formed. You go and do a Raman spectra, and you will be knowing that okay, whatever material I have made, it is MOS2 or gallium nitride or whatever it is. And one more thing we can do is that stress or strain analysis. So nowadays, as we know, we are moving to the nano world. So nowadays we are making the thin films of the material and nanostructures of the material. So what happens in these nanostructures and all? So there will be some strain because of the relaxation and all. So we have to analyze that strain. So we have to see in our material how much strain is there, because these strain and all, it affects the at last we are going to use this material some device purpose and all some practical application. So we have to see analyze the strain that will be affecting our property device properties and all. So we have to analyze that strain. So what happens in Raman spectroscopy, if you can study this peak weight. That peak weight gives the strain or sorry, that change in the peak position gives in the strain or stress analysis. Let's say in normal that bulk crystal or single crystal silicon, we find the peak around 520 centimeter. So if my material I have made a thin film and it's not coming at 520 or it's coming around 525, then I can expect there is a strain, and from that shift, how much it has shift in 5 centimeter or 10 centimeter or 2 centimeter or 10 centimeter. From that shift, I can calculate how much strain is there in my material. Similarly, one more important thing we can do, that we can perform the polarized Raman measurement. Polarized means you can polarize the incident light as well as whatever scattering light we are detecting through the detector. Before that, we can put a polarizer so that we can perform polarized measurement. So by performing a polarized measurement, we can determine the crystal symmetry orientation, like in hexagonal or cubic or this kind of things. We can see that we can perform that crystal analysis using this polarized Raman measurement. Similarly, if we analyze the width of the Raman peak, we can tell the quality of the crystal. So in general, if the peak width is very less, then we tell that it is a very good crystal. And if it's broad, then we tell that it is the crystal quality is not that good. And as I can mention that in case of the amorphous, there is no crystal symmetry. We get a very broad peak in Raman. And one more thing is that if we analyze the intensity of the peak, so it is directly proportional to amount of the material. So if the intensity is very high, then we can tell that amount of material is high. And so this will be useful when we are analyzing like a mixture of two materials. So we made some composite and we want to see how much it is not exactly the quantitative, but relatively we can tell from the intensity that okay, I made a composite of two materials. So this material maybe silicon germanium, I made some alloy. So if the silicon peak intensity is relatively high than the germanium, then I can tell that the amount of silicon in the alloy is greater than the amount of germanium. So basically this is a relative calculation, not exactly the quantitative analysis. So these are the 4-5 important things we can do with the Raman. Apart from that also, there are several other things which we can perform using the Raman spectroscopic analysis. So I will be giving one of my PhD work example. So here I have studied the vibrational properties of 3,5 nitride nanostructures. So yeah, and one more thing I just want to mention. Sorry. So how many peaks, like we call how many modes in the Raman spectra? So if there are 5 peaks, we generally call that these peaks as modes. So what are these things? They are vibrational modes. Like in this typical example I am giving in case of the 3,5 nitride, where we have in the primitive structure, we have 2 atoms from the group 3, that is denoted as the big bonds, and the 2 atoms from the group 5. So generally here I will be talking about if it is gallium, other one will be nitrogen, a smaller one. So this is assigned as A1 mode. So this is particular type of vibration. So 2 gallium nitrates, gallium atoms are going one direction, and 2 other nitrogen atoms are going in different direction. So this particular vibrational pattern is called as a A1 mode. Similarly, other modes are there. So how many modes will be giving the Raman signal? How many modes will be appear in the Raman? How many modes? There are several vibrational modes. Some will be appearing in Raman, some will be appearing in IR. So these analysis we can perform using the group theoretical calculation. So group theory, and by using the group theory analysis, we can predict how many Raman modes will be present in my sample. So that is a little bit calculations and all we have to perform. So that is something different topic. I don't want to go to the details. So here since I am giving a particular example of 3,5 nitride, here group theory predicts there are one A1 mode, 2 B1 mode, and one E1 and 2 E2 mode are present at the zone center. As I told that in the earlier, we will be probing the phonon at the zone center only. So among these predicted modes, E2 mode is the Raman active mode. A1 and E1 modes, both Raman and are active. And A1 mode is polar, and E1 mode, they are polar in nature. Polar means with the incident light, they split into corresponding longitudinal and transverse optic modes. And the B1 mode is completely silent mode. That means it doesn't appear in Raman, either in Raman or IR spectroscopy. So that's why it's called as a silent mode. We cannot probe on the B1 mode using Raman spectroscopy. And one more thing, the important thing we can do with these polar phonons. As I told that A1 and E1 modes are polar modes. That's why they split into corresponding L1 and 2. So if the material has polar phonons, and one good thing with these polar phonons that they can couple with the carrier, like electron. If your system has electron or holes, that is the free carriers, it can couple with that. And if you perform a Raman spectroscopic analysis, then we can calculate the carrier concentration by analyzing the polar phonon mode. So that is a very good technique. So if we want to characterize the free electrons in the system and all, we have to perform Hall measurement and all. And in single nanostructure devices, carrying out a Hall measurement is a little bit difficult, and we have to do so many things and for them processing, material processing. So that's why this Raman is a very powerful technique in this particular sense, and we can calculate the free carrier concentration also. So that we have done. We have made 3 gallium nitride samples with varying the gallium to nitrogen ratio, and from that we can see that there is LO, A1 LO, which is coupling to the electron. So I just don't want to go to the complete details. Just I can emphasize that by using the Raman analysis, this is the uh, mm, uh, correlation factor we have used, and by analyzing this correlation factor, we can calculate the electron density as well as mobility in the system, and that we have calculated. So with the increase in the gallium to nitrogen ratio, the carrier concentration is increasing and the mobility is increasing, so on and all. So here what I just want to mention, emphasize that, so by using Raman also, it is a very powerful technique. So whatever I have mentioned in the last slide, there are the basic things, the primary things, 4-5 primary things we can do in every material. So in some materials, by using this property, like where polar phonons and they couple with the carriers. So by in this some particular cases, we can do more than from the normal things what we do using the normal spectroscopy. So here we have calculated the carrier concentration by using the Raman spectroscopy, which is the then now this is the things by using Raman spectroscopy what we can do and what are the things I have just discussed. Now we will move to the nanospectroscopy. Why we need nanospectroscopy? That is the first question. Already we have done the spectroscopy and we analyze the material, we got several properties and all. And now why we should go to the nanospectroscopy? So now the thing is that now our society is moving to the nano world. All the devices are and all. Starting from the you may be knowing that LED light emitting diode. Now they are using the thin film of the material. So now research is going towards the nanoscale, and how we can use the nano layers or nanostructures or nanomaterial to use in different devices, so that we can get better performance and better efficiency in the devices and all. So before going to the device application, we have to completely characterize the material. So if there is a nanostructure, we should spectroscopically perform measurement and see all the physical properties, so that we can get best result out of that when it is going for the device application. So that's why we should perform some nanospectroscopic measurement. Why it is important? So as in the past lecture, Dr. Shivadasan has discussed that there is a resolution limit, that is the diffraction limit, which is governed by this Abbe's diffraction limit law. So what this Abbe's diffraction limit tells that we cannot focus light up below a certain limit. So that limit is called as the diffraction limit, and it is given by this formula. Delta x is 0.6 lambda by numerical aperture of the optical system what we are using for the focusing. And this numerical aperture can maximum go up to 1. So roughly we can probe lambda by 2. We cannot go below lambda by 2 to focus a light below that. So generally if you use the visible light, we can maximum go up to 200 to 400 nanometer. In that range we can focus the light and we can perform the spectroscopic measurement. As I told, in the spectroscopy measurement, in Raman or IR, mostly use the visible range, visible to IR range, and in that range we can maximum go below the limit of 200 to 400 nanometer. So now in nanostructure, generally we tell the nanostructure if it's below the 100 nanometer scale. So if I have a nano wire or structure or film which thickness is 100 nanometer, so it will be very difficult for me to focus the light to the 100 nanometer system and take the spectra. That's why in optical spectroscopy, we as I discussed, because of the Abbe's diffraction, it prohibits for going to the higher spatial resolution. As I told, we using the visible, we cannot go beyond 200 nanometer, but my system is only 100 nanometer or below that, 50 nanometer or 60 nanometer. So how I will do? So what happens if we take a ensemble of the systems and do. So whatever property, whatever physical property will be getting, that will be ensembled average. We will not getting the information from a single nanostructure or a single nano device which we are going for the practical application. So we cannot precisely characterize a nano device. So that's what I want to emphasize, that if we have a nano device or a nano structure and we want to spectroscopically analyze these and go for a practical application, we cannot, this spectroscopic technical limits, the Avex diffraction limit prohibits us to characterize the nano device precisely and get the physical property or chemical properties or whatever it may be. So that's why what we have to do, we need to perform nanospectroscopy. So what we have to do, we have to modify the conventional spectroscopy in such a way that we can go beyond the nano limit, and there we can go and we characterize our material in the nanoscale, so that we get all the properties whatever are there in the nanoscale. And one more thing I just want to tell, that as you know, all the nanomaterials, they behave differently from their bulk counterpart. So it is very important to characterize the nanomaterial. So we cannot just take the bulk property or bulk value for the material and go for the device application and all. So we have, it is very mandatory and very important to characterize the material at nanoscale. So we need to perform nanospectroscopy. Now we will be discussing how we will design the nanospectroscopy from the conventional spectroscopy technique, how we will go from the nanospectroscopy. So this is the slide where we will be talking about the designing of the nanospectroscopy, how we will design. So now, as I mentioned, that only thing is that it has the capacity to probe the system, but it cannot give a special resolution down to nanometer. So what we have to do? So we need to couple this spectroscopic conventional spectroscopic system to a system which is having a very high spatial resolution. So that is the key point. We have already a spectroscopic technique. Now we don't have only the spatial resolution. Now what we can do? We can couple with a system which is having the high spatial resolution. Then only our purpose is solved. So that is the and nowadays one important technique is that atomic force microscopy. What this atomic force microscopy do? It gives a high resolution topography down to even to a 1 nanometer, 2 nanometer range, practically to the angstrom level also, we can get the surface topography of a sample. So the atomic force microscopy gives us the high spatial resolution down to the nanometer. Now, as I discussed, this Raman spectroscopy, it gives different properties, as I have discussed, this chemical, mostly this chemical composition, crystal orientation and all. So what we do, we can couple this AFM as well with the Raman. So the analytical capacity of Raman will be using, and we will be using the spatial resolution of the atomic force microscopy. So this spatial resolution of atomic microscopy and the analytical power of Raman, this all both together will be giving the high spatial resolution microanalysis. So now we can perform the spectroscopic measurement down to the nanometer scale by coupling these two techniques. So before going to this coupling, I will be just a few slides. I will be giving this basics of AFM, how it operates, what are the different modes and all. So yeah, before going to that, I just want to give a feel that why you should go for this nano and all. So this is a nano device. This is a single gallium nitride 2-terminal nano device, which we made in our lab during my PhD period. So this is a single nanowire, and this is the IV characteristics plot of this material. So this is the electrical characterization, of course. So if you want to see the compositional analysis and all, we should perform the Raman measurement or something like that to probe, we have to see how uniformity the property is varying throughout the nanowire, because at last we are going to use this as a device. So that compositional uniformity, the stability and all, these are the important things we should perform. And these are the few advantages I have listed, which are the, as I already told also, these are the few advantages in the nanoscale devices. So they consumes very less amount of material. The efficiency of these nano devices is very high, and they of course consumes very less power, and making this nano device also will reduce our production cost. So just to give a glimpse of this nano device and all, I just presented the slides. So the now later we'll be imaging this single nanowire using the tip enhanced Raman spectroscopy. I will be showing you later. So now we'll be going to the AFM technique. So this is the basic what happens in AFM is there is a small tip. The tip apex will be around 10 nanometer or 5 nanometer in that range, or sometimes in 20, 50 nanometer also. So what happens that tip, that is the tip which will be probing the interaction between the sample and the cantilever. That is, the tip is basically a cantilever, and the end will be a sharp tip, which will be, the size will be few nanometer. So what happens? It generally operates, the working principle is it governs the Hooke's law. So the cantilever will be vibrating near to the sample. So with this vibration, it will be probing the sample surface, and with this information, we will be getting the sample topography. It will be scanning throughout the sample. So by point, it will be interacting with the sample. From that interaction, we can get the topography of the sample. And this is our Lennard-Joule potential curve. So this is the Lennard-Joule potential formula is given. So there are three different regimes, as we know. So this is the interaction curve between the tip and the sample. So by dividing into three interaction portion, we can perform three types of atomic force measurements in three modes. One is the contact mode. In the contact mode, the tip is almost touching to the material, and the distance between the tip and the sample is less than even 0.5 nanometer. So, and this is the intermediate zone. Intermediate zone. What here? What will be happening? That tip sample distance will be 0.5 to 2 to 3 nanometer in that range. And one more region is that is the non-contact mode. Here the tip sample distance will be more than 2 to 3 nanometer, and up to, it can go up to even 10 nanometer also. So this is the here in this region, what happens? The tip sample interaction is attractive mostly, and here both attraction and repulsion can happen, and in this region the tip sample interaction is mostly repulsive, and this all this interaction, that is the van der Waals interaction. So here no other forces act. So only we probe the van der Waals interaction between the tip and the sample, and this that gives the high resolution topographic image of the material. So as I have discussed, there are different modes. There is a contact mode, intermediate contact mode, and non-contact mode. So here in contact mode, the tip is mechanically completely attached to the sample, and as I told, the interaction is repulsive. In the contact mode itself, we can work in two different modes, that is the constant force modes and constant height mode. In constant force mode, what happens? We will be by the feedback mechanism, we will be giving a constant force to the tip, so that every time there will be a constant force between the that is the van der Waals force between the tip and the sample. So to maintain that constant force, so it will be going up and down, and from that we will be getting the surface topography of the material. So similarly, in the constant height mode, the tip will be at a constant height from the surface, and by scanning the throughout the sample, we will be getting the topography. Then now this is the schematic, how it gives the image of a material, the topography, how it gives the topography. What happens? In the cantilever top, there will be a laser shining to the top of the cantilever, at the tip of the cantilever. Once it moves here and there, according to the topography, it will be going up and down in the material. So if it's going up and down, the reflected laser beam that goes to a 4-quadrant photodiode. So initially we will be fixing this point to the mid of the photodiode, so that the output current completely will be 0. So once it's go up and down while scanning the sample, depending on the sample roughness, it will go up and down. Then what happens? The position of the reflected laser beam will be changing. So once this position will be changing, then in the photodiode, the as you can see, this position will be reflect. If it's up, then it will go up. If it's down, it will be going down and on. Then the output current from the photodiode will be different. So that will be positive or negative, whatever that amount. Then what happens? We have a feedback system and the amplifier, lock-in amplifier and all. So what happens? They take this signal, and from this output current, then it reflects as a topography of the material. And there is a of course a piezo actuator which tries to give the feedback to the sample. And this is the intermediate contact mode. This, as I told, it is neither operates in the repulsive or attractive zone. It operates in the mid of the zone, and this basically this is applies to a biological sample, because in the other one, the contact mode, so it is almost the tip is touching to the sample. So if it's a biological sample, it is they are very sensitive. And so what happens, the tip may damage the sample, and sometimes what happens, the sample also gets stuck into the tip, and tip will be damaged. So for biological sample, we generally perform the intermediate contact mode, so the tip will be not exactly touching, so it will be vibrating just above the sample, in between 2 to 3 nanometer, in that range. So this is the advantages of the intermediate contact mode. It can apply to wide range of sample. So by using this intermediate contact mode, I can show this is the typical gallium nitride nanowires, which we have performed the AFM measurement on the nanowires, and here we can see there are wide range of diameter of nanowire. So starting from 10 nanometer to 40 nanometer, and the maximum nanowire diameter is 60 nanometer, and this is the AFM topography of the sample. Similarly, as I told, this non-contact mode here, it works in the long range van der Waals force acts and in the attractive zone. Here what happens, the area of interaction will be very less, since it is far away from the sample, the area of interaction will be very less. So other side of the material don't contribute to the force, so we can get the true atomic resolution or true surface topography of the sample. So now with this, now this is the typical instrumental setup. Here is the sample. Here the laser diodes incident on the tip, top of the cantilever, and it reflects to the 4-quadrant photodiode, and it gives to the error signal. And with this, it goes to the piezo actuator or the piezo scanner. Here it maintains the feedback, and from this we get the surface topography using a computer. So this is the things. And one more thing I just want to tell, apart from these cantilever based tips, there are also tuning for based tips. In the cantilever based, what happens? We incident a laser on that tip, and the reflected light goes to the 4-quadrant photodiode, and we take the measurement. However, in some experiments, like since we are going to do couple with it with the Raman spectroscopy, there is additional laser. One more laser will be probing the material. So there can be interference of this laser and the other laser coming from the Raman. So that's why we have to avoid that kind of things. That's why what we do, we use the tuning for best tips. So what happens? The here you can see the AFM tip is connected to a tuning fork. What happens? The tuning fork will be some natural frequency, as we know. So it will be vibrating. If you apply some voltage, it will be vibrating with a natural frequency. So once it comes near to the sample, the natural frequency changes, or the amplitude of the tuning fork changes. So according to the change in the vibrational frequency or the amplitude of the tuning fork, we can take the surface morphography as a function of this change in amplitude or change in frequency. So there are two, according to that category, there are two modes. One is amplitude modulation AFM, another one is frequency modulated AFM. So as I told, this amplitude modulated AFM, it denotes the, it takes the value change in the amplitude of the vibration of the tuning fork. Similarly, in frequency modulated, we take the change in the frequency, and it converts to the surface topography. So now we'll be discussing about the nanospectroscopy. So as I told, in nanospectroscopy, we have a coupled system. We have AFM as well as we have Raman. So we couple both AFM and Raman to break the diffraction limit, and really we have to go to the nano region. So here what happens? So this is the AFM tip. So this is not only a normal tip. Here one gold nanoparticle will be attached to the tips. Why a gold nanoparticle is attached? As we know, this gold or silver, they are plasmonic materials. So as Dr. Shivasan has talked so much about the plasmonic material and how this plasmonic materials enhance gives the confined light and all, we can get, so we can go to the really diffraction limit. So here we put a gold nanoparticle. What it does, by using the plasmonic property of this gold nanoparticle, we can localize this, whatever that incident laser will be coming. So this is the laser path coming from the AFM system. I will be in next slide. I will be showing the diagram. So here in this path, the incident laser will be coming. So what this plasmonic property of this gold nanoparticle does, it localizes the electric field and enhances the electric field. There are two things. It enhances the electric field as well as it confines the electric field. So once it enhances the electric field, we will be getting a better signal. Since getting a Raman signal, as I told, it's an inelastic scattering. So the getting a signal from a nanostructure is very difficult. So if you want to do a Raman spectroscopy in a single nanostructure, one thing is that we have to focus. The second thing is that we have to get some signal also. The signal should not be very poor. So that two purpose is solved by putting a gold nanoparticle, that plasmonic particle, or some cases also the plasmonic material is coated on the tip. So here in our case, this is a gold nanoball attached to it. So what is does, the metallic nanostructure, what is does, it enhances as well as confines the electric field. So these two things it's do. So once it's confines the light, then we can go on this confinement. So it will be depending, not now, it will not be depending on the what the numerical aperture you are using, what are the excitation laser you are using to the Raman. It will not depend on that. Now it will be depending how the particle size you are using. So, and sometimes it can go below the 10 nanometer region also. So now it can confine previously the Abex diffraction limit, we are not able to go beyond the 200 to 300 nanometer and all. So now we can go below 10 nanometer also. So now we can truly perform the nanospectroscopic measurement at nanoscale. So, and one more important thing also, we will get a enhanced Raman signal so that we can characterize our material in a better way. And if we perform this measurement throughout the sample, if we raster scan this a single nanowire we can take and we can raster scan this material, then we can get a spectroscopic imaging also. I will be showing. So we can get a spectroscopic imaging, and it will be coming as a touch mapping or touch image of a single nanostructure. So this is the typical setup in our lab. So this independently is a Raman spectrometer, and we can perform the Raman measurement independently. Here you put the sample, laser in the backside, it comes, and here the CCD is there, we get the Raman signal. And similarly, independently, if we see the AFM system, this is the AFM system, this is the sample chamber. If you zoom this looks like this. Here we put the sample, and here we mount the, there are 4 towers, anywhere you can mount the tip. So you mount the tip here and we perform the normal AFM, you can get the AFM. So now the coupling comes. So here the laser from the spectrometer can go through this path. This is the coupling path, and it can incident in the system. Here are here we will be keeping our sample. So now the laser can go in this path and incident on the sample, and in backscattering setup, exactly it can come back, and now we can detect the scatter light through this system, and we can detect here in the same CCD. So now what happens? Now we are not taking the measurement now only with the Raman spectrometer. We are coupled to the system with the AFM tip, which is near to the sample. As I discussed, that AFM tip is connected to a gold nanoball, plasmonic nanoball, and it enhances as well as gives a spatial resolution down to the nanometer. So by using this coupled system, we can break the resolution limit and we can characterize a nano device spectroscopically. We can image, we can get the structures and all. So these are the few examples. So this is the example from literature. What they have done, they have this is a single wall carbon nanotube. So in different position, they have impacted strain by using the tip, and in different position they have taken the Raman spectra. So there are 1, 2, 3, 4 positions they have taken, and the Raman spectra is different in 4 different positions. This is basically the same material, but the spectra is different at different position just because of the strain, and from that they have calculated how much strain they have impacted by analyzing this Raman spectra at a different position. And this is the typical gallium nitride. This is the first time touch study in gallium nitride nanowire. What they have done, they have taken a single nanowire, and without the in normal Raman spectrometer, they don't get any signal from a single nanostructure, since it is a inelastic scattering, and scattering cross section is very low. So once they use the tip enhanced Raman spectroscopy, they could get the signal from the. This is the characteristic of the single gallium nitride nanowire. So they could get the Raman signal from a single nanowire. Similarly, in our lab also, we have characterized the magnesium doped P gallium nitride. Here, without the tip, we can see there is the black line. There is no single Raman signal. Once we bring the tip and take the measurement, the signal get enhanced, and here we see a local vibrational mode, which is because of the magnesium doping, and from that we confirm that okay, the magnesium doping is there in a single nanowire. So this is the study. Now I'll be talking about the more touch imaging, how we perform in our case. So this is the AFM of a single nanowire. In the absence of tip, this is the black line. We see a less intensity Raman signal. Once we bring the tip and take the signal, so we see the red line. This is the signal in the presence of tip, and we have deconvoluted into 3 peaks, and we have see there are 3 modes and all. So and we have calculated, as I told, that there will be enhance in the Raman signal. We have calculated the enhancement factor using this formula and so on. So this I don't want to go to details. So now one more important thing is that what we did by this is the typical AFM spectra. What we do, we have taken the Raman spectra at each and every position, and we converted that into a image. So this is the TARS mapping. This is the spectroscopic map. So this is the typical AFM, and this is the spectroscopy. And in the tip of the nanowire, there is a gold, so which doesn't appear as in starting itself. I have mentioned Raman doesn't probe metallic things and all. So the gold doesn't come here, and we see a single gallium nitride. So this is the typical TARS map. So if we apply this Abbey's diffraction limit according to our setup, if we calculate the diffraction limit, we cannot go beyond 750 nanometer. However, using this coupled system, using this nanospectroscopic imaging technique, we could image a gallium nitride, single gallium nitride nanowire, which is having diameter of 200 nanometer. So this is the beauty of this technique. Really, you can break the diffraction limit and go to the nanoscale regime, and you can characterize the nano devices precisely with a high spatial resolution. And from this analysis, we can see that there is a compositional uniformity and all throughout the gallium nitride nanowire. So with this, I want to thank my team members. This is our team. This was our team in IGCA Karpakam. So this, thank you everybody. And I will also like to attend if somebody having any doubt or questions. Thank you.
Okay, thank you very much, sir, Dr. Sundar Kumar Parida.
Thank you. Thank you.
And just I would like to ask us few questions just for some academic purposes.
Yeah.
First, I want to know if you use far field spectroscopy for measuring Raman spectrum, and if you are taking the same sample for a near field spectroscopy, then is there will be any difference in far field and near field? Whether we can expect some difference in that in spectroscopic aspects?
Yeah. Spectroscopic, as I told, in far field measurement, you will be getting a ensembled average. So the as I have shown one example, like a single wall carbon nanotube they have taken. So if you take a single wall nanotube and take a far field measurement, what happens? Whatever I have shown here. So you will not be getting difference, whatever that different position they have taken. We will be getting like position 2 or 3, or if you repeat the measurement, sometimes you will be getting the signal which is be looking like 2 or 3 or 1 or whatever maybe, but we will not be getting a distinct things. The spatial resolution, that is the main thing I just want to think. The spatial resolution will not get. So if you want to see that how uniformly strain is distributed in a single structure, how the compositional is throughout my sample, then we have to go for the down to the nanometer, and you have to perform the nanoscale measurement. That is the thing. So that will be the difference.
Okay, one more question. Actually, you have said something about some enhancement factors.
Yeah.
Okay, so the whether this enhancement factor is purely depends on this plasmodic enhancement, or is there any other factors which can influence the enhancement?
Yeah. Actually, that two, three things are there. The
Yes, yes.
tip sample direction also. The polarization, if your polarization of laser, incident laser on the tip axis, they are in parallel, then you will be getting more enhancement. So if the tip is having some angle with the polarized laser, then the enhancement factor will be little less. So that is one factor. And the one more thing also, the material also. Generally, this covalent material, they gives higher polarizability, and we get higher enhancement in that case. And in this ionic crystals and all, as I have shown in galvanited, the enhancement factor is not that much high. It's very less only. So because but in organic samples and all, people used to get order of 10 to the 4, 10 to the 5 in that order also. So in our case, it is only one order high. So it is so that is also one more factor which decides. These two factors mainly decide the, apart from these things in this plasmonic enhancement. Those are the two factors decides the enhancement factor.
Okay, sir. Thank you. I have one more general question. Actually,
Yes.
this IR as well as Raman both are in the vibrations modes. But
Yes.
what are the advantages of Raman over this IR in terms of sample preparation or something like that? Can you just
Yes.
deliver some few words about it?
Yes. Actually, in all, like in thin films and all, directly you cannot go and do the IR. Of course, nowadays that systems are available where you can go, but in Raman, there is no sample preparation at all. So as like you made your sample, you can go and do the sample. But in IR, you have to do some, you have to change the mode of collection and all. Sometimes they will do in, if it's powder sample or a pellet, they will be doing transmission mode. If it's like a thin film and all, they will be going for the reflection mode and all. So according to the sample, they have to change the mode of collection and all. But in Raman, nothing to do. Just go and put your sample and take the spectra.
Okay, thank you, sir. It was a very nice talk, and the session is open for the audience.
Thank you, sir.
Participants are requested to ask their questions. You can type your questions in the chat box, or you may unmute yourself and ask questions.
Sir, one question from the chat box. Where is Raman spectroscopy used? Hello?
Yes, sure. Raman spectroscopy, as I told, it is used in from wide range of things. Like in physics, we use to see the material characterization. So the material, I have made a material. If it is in which phase, in cubic phase, tetragonal phase, what material it is. So is there, so like a XRD we perform to see the phase formation and all. That is similarly Raman is also one type of basic characterization tool to see the phase formation and all. And the second thing also in chemical things, also in chemistry also people use. This is the molecular vibrational things and all. They see. And of course in biological sample also people perform Raman spectroscopy. So this Raman spectroscopy has wide range of application from starting from physical science to chemical science and biological science as well. Am I clear or hello?
Hello, is there any more questions? Hello? Participants? Okay, I think questions are over. Feedback link will be posted in the chat box. All are requested to fill the feedback link without fail. It will be considered as your attendance form also. The next session will begin at 11 o'clock. Thank you, sir. Thank you. It was an informative and engaging talk. We could broaden our knowledge about spectroscopy, Raman spectroscopy, and diffraction limit in spectroscopy, etc. Thank you, sir. We will join you at 11. Thank you.
ശരി അവിടെ പോവല്ലോ അല്ലേ ഞാൻ കുട്ടികൾക്ക് വരാൻ ഞാൻ ആ അതെ അതെ ആ
Welcome back to our session. The second session is about application of nanophotonics in miniaturized devices. Ms. Soumya K, Senior Research Fellow, CMET Athani, has joyfully accepted our invitation. Welcome to Ms. Soumya K. Over to Soumya.
Thank you, ma'am. Thank you.
Soumya has
Thank you.
is doing research in investigation of plasmonic properties in oxidized and nitride films. Welcome to Soumya.
Thank you, ma'am. Thank you. Am I audible and my presentation is clear? What about?
Yes,
Hello?
it's audible.
Yes, audible.
It's audible and it's very clear.
Okay. So thank you for your warm welcome, ma'am. And I am also thanking you for considering me as a part of this program. So good morning, everybody. I'm Soumya from CMET. CMET is an R&D institute under the Ministry of Electronics and Information Technology. Its headquarters is in Pune, and we have branches in Thrissur as well as Hyderabad. And I am working as a CSIR SRF under Dr. S.N. Putty, and our work is mainly concentrated on thin film plasmonics. So the mission of CMET is to develop knowledge base in electronic materials and their processing technologies and become a source of critical electronic materials and know-how and technical services. And CMET has certain objectives. That means to establish technology up to pilot scale for a range of electronic materials and transfer the same to industry for commercialization. And since 80% of the electronic components in India are importing, to support strategic sector also, CMET is doing some works. And CMET is open to public on every science day. So please visit CMET on coming February 28th and understand what all activities are happening there. So today, I would like to discuss you about applications of nanophotonics in miniaturized devices. So, I think the word miniaturization have large impact in this modern world because we humans basically need all the technologies to hold in our single hand. So, before going into the topic, I think I would like to remember you the path of miniaturization of a computer that we are using in our day-to-day life. So we all know that the first generation computer was based on vacuum tubes, and it consists of almost 20,000 vacuum tubes, and it weighed more than 27 tons, and its length was almost 30 meter, and its height was almost 2.5 meter, and it occupied almost 1,800 square feet area, and it consumed almost 150 kilowatt of electricity. And after the invention of transistors, the second generation computer came, and it was 1959 to 1965. And compared with the first generation computer, the second generation computer consumed less power as well as they were more compact in size, more reliable as well as faster. So in again, third generation computer came and it was in 1965 to 1971. And here, instead of transistors, they used integrated circuits. And in single IC consist of so many resistors as well as transistors. And again, compared with the second generation, the third generation computer was more compact, reliable as well as fast. And the third generation was again developed into fourth generation computer, and it was in 1971 to 1980. So here they used the VLSI circuits instead of integrated circuit. That means very large scale integrated circuits started to use, and actually it contains 5,000 transistors and other circuitry elements. And the concept of microcomputers was also started in this fourth generation, and also the revolution of personalized computer was also started in this generation, fourth generation. And again, compared with the third generation, this fourth generation computer became more powerful, more compact, more reliable as well as more fast. And now we are actually in the fifth generation, and it actually started from 1980 to till this date. And in fifth generation, this VLSA technology became this ULSA technology. That means ultra large scale integration technology, and it resulted in the production of microchips having 10 millions of electronic components And some computers of this generation were desktop, laptop, notebook, etc. So what I want to tell is, due to technology development and along with the miniaturization, this room size and temperature was transformed into handheld devices. And while considering the mobile phones also, we can see this difference. And the first handheld cell phone was sold on the market by Motorola by a name named as Martin Cooper. And this phone was named as shoe phone. You can see the picture of this phone here. And this phone was almost as big as shoebox, and it allowed user to talk only 35 minutes, and it required almost 10-hour charge. So Cooper, in one of his interviews, said that he was very much excited to announce this, and he just went to the streets of New York and thought, whom should he call first? So the first name came to his mind was his competitor at the AT&T company. I think this was a famous American telecommunication company. And what he said first was quoted here, that hello Joel, Martin Cooper here. I'm calling you from a cell phone, a real cell phone or a personal handheld cell phone. That means he was that much excited to tell the community that he actually invented the first cell phone. And today we all are addressed by some numbers was possible due to the invention of this first handheld cell phone by Martin Cooper. So next I am considering some advantages of miniaturization in engineering aspects. So if a system is small, we can actually move or stop more quickly than the larger system due to its low mechanical inertia. And again, for miniature system, there will be less thermal distortion as well as less mechanical vibration. And if it is small, then it will be suitable for biomedical as well as aerospace applications. And small system have higher dimension stability at high temperature because of low thermal expansion. And again, smaller size means less space requirement, and this feature allows packing of more functional component in a single device. And again, if our material, sorry, if our component is small, that means we require only less material, and it also means low cost of production as well as transportation. So today we are considering the role of nanophotonics in miniaturization of devices. So this was a presentation include the topic like what is nanophotonics and why we need nanophotonics, how this nanophotonics helps in miniaturization, and what are the applications of nanophotonics, etc. So moving to the first topic, what is nanophotonics? Nanophotonics or nano-optics or plasmonics is a part of nanotechnology that investigate the interaction of light and free electrons on a nanometer scale. Or making it more simple, it is the it is the combination of electronics as well as photonics in a nano dimension. So while talking anything about nano, we cannot start with a name called Richard Feynman because the first ever concept of nanotechnology was given by him in 1959, and he's a professor in physics. And his famous quote about nanotechnology is, "There is a plenty of room at the bottom." And a great emergence in nanotechnology was also happened after in 1980s because after the discovery of scanning tunneling microscope in 1981 and discovery of fullerene in 1985. So the reason why we need nanophotonics was due to some limitations of photonics, such as its difficulty to focus light into nanometer scale, and this difficulty was due to the diffraction limit of the optical components. And what is diffraction limit? That is I showed. That is I quoted here. The size of the optical mode propagating in a conventional dielectric waveguide cannot be smaller than approximately half of the wavelength of the material in which the light is propagated. Or making more simple, we can tell like that if we are propagating a wave having wavelength lambda, then the minimum lateral dimension possible for the optical component will be lambda by 2. So to improve the integration density, one need to break this limit, but as well as optical components are considered, we cannot break this limit due to diffraction limit. So we need an alternative solution. And thus the other possible solution was using nanophotonic techniques or plasmonic techniques using the surface plasmon. So, like electron in electronics and photon in photonics, here in plasmonics, we have plasmons are the fundamental particle, and they are the quantas that is associated with the collective excitation of free electrons in metals when it is interacted by a light. So I already told like that it is the interaction of photon with the free electrons. So since metal were considered as the granary of free electrons, they are the conventional plasmonic material. And again, plasmon can be described like a collective wave where large number of electrons oscillate in a particular synchronization. And unlike photon, this plasmon do not have a diffraction limit so that they can travel along nanoscale material. So we already understood that nanophotonics is nothing but the interaction of photon and electron. So the question is, does plasmon can be generated by simply illuminating a photon with an electron? The answer is no, because for coupling to take place, there should have a momentum matching between electron as well as a photon. So in the left figure, show that momentum of the photon is less than momentum of the excited electron. So there is plasmon generation, but when these are equal, the surplus plasmons are generated. So we can consider some methods to make this momentum match. So what we are doing is we will consider a light and we'll pass through a prism cup, triangular prism, and where the base of the prism is coated with a plasmonic material. And before reaching the light into the prism, it was passed through a P polarizer so that it became TM polarized light. So I think there will arise a question like why we need TM polarized, why not TE polarized light? So if we consider this direction as X and this direction as Z, then for TM polarized light, the magnetic field will be perpendicular to the plane of incidence so that we get dy, Ex as well as Ez. So if it is T polarized, then we will get Bx and Bz and electric field will be in the y direction. So for the surplus plasmon generation, we actually need Ex and Ez. We actually need electric field component to be in this plane only. So this electric field will couple with the excited electrons on the surface of the plasmonic material here. Here. So this photon which is passing, here we can see the momentum equation of surplus plasmon as well as photon. And here in the momentum of photon we can see a sin theta term. So for an SPR to generate, we already understood that these two momentum should be equal. So so we can actually tell like that by varying the theta, here we have sin theta term. So by varying the theta, we can actually shift the momentum of photon to be equal to momentum of electron. And the sin theta in the momentum of photon comes because we are eliminating light at a particular angle theta. So here we will have parallel as well as perpendicular component. So and here we are
കുറച്ച്
interested in
ആളുകൾ
the parallel
ലീഗറുണ്ട്
component because
ഇതിലെ റോഡൊന്നും ഞാൻ ആ സ്ഥലത്തിന് പിന്നെ ഒരു പ്രസക്തി ഉണ്ടാവില്ല, അവരങ്ങനെ വളച്ചു വിടുന്നതാണത്.
hello. Okay.
Sorry, madam, it's just a disturbance. You can continue, no problem.
Okay. And by changing the theta, we can actually change the momentum of photon, and thus for a particular theta, coupling take place, and hence SPR can be observed.
അന്ന് റേഷൻ കടയിൽ ഓണറായിരുന്ന ആളാണ്.
So again, another very important thing we need to understand about SPR is it will generate only for an angle greater than the critical angle, because total internal reflection plays a major role here. So when a total internal reflection take place like here, an evanescent wave will generate and it will actually move from here to here, and it actually couple with the free electrons present in the surface of the plasmonic material. So actually so far we discussed the interaction of photon and electron, but now we understood that photon was not directly involving in this coupling, but it was done by the evanescent wave. Since evanescent wave decays fastly while moving, the thickness of the film should be minimum. Then only we can reach at the film surface and couple with the electron. So in prism coupling, we can actually couple in two different ways known as Krushman as well as auto configuration. And here the substrate is stick to a prism. In Krushman configuration, the substrate is stick to the prism using a refract index matching fluid. But in auto configuration, the substrate is not sticked but kept at a certain small distance in nanometer range. And in Krushman configuration, the evanescent wave produced here should reach at the film dielectric interface so that the thickness of the film should be minimum. But in auto configuration, the evanescent wave is producing here, and to reach from here to here, the distance between the prism as well as the plasmonic film should be minimum. So in Krushman configuration, thickness of the film should be minimum, and in auto configuration, thickness doesn't matter, but the distance should be minimum. So most of the researchers use Krushman configuration for the generation of the surplus plasmon resonance. So other methods to generate surplus plasmon resonance are using optical fiber, because optical fiber, we know that it consists of a core as well as a cladding. So it is actually guiding light through by a technique known as taut inner reflection. So if we consider like that, if you remove some portion of the cladding and if we got a plasmonic material here, and what will happen is the evanescent wave generated due to the taut inner reflection will couple with the free electrons on the metal dielectric interface, and it will also result in the surplus plasmon resonance. And surplus plasmon resonance can be generated by grating, and the incoming photon at an angle theta with respect to the normal to the surface of the metal can undergo scattering due to grating, and which will increase or decrease the wave vector of the incident wavelength by integral multiple of grating wave vector, and this result in the diffracted order. So generation of the evanescent wave happens when this wave vector of the diffracted order kg was greater than incident light wave vector. That means if kg is greater than k0, evanescent wave will happen. And the coupling condition for the incident wave as well as the evanescent wave as well as the free electron was showed here. If this equation is satisfied, then the surplus plasmon resonance will be generated. And also the period and amplitude of the grating also determines the resonance frequency here. And this figure shows the schematic representation or schematic diagram of a surplus plasmon wave. And the light incident on the material will result in shifting of charges, or we can say that the material get polarized when it is interacted with the material with the light. So we will discuss about this more in our next few slides. So the beginning of the surplus plasmon resonance was in 1902 from Wood's experiment, and he observed a anomalous behavior in reflected beam from the diffraction grating. And what he observed was he written here. This grating at a certain angle of incidence will show one of the D lines and not the other lines. So what he observed is a dark band for a particular wavelength, and he was not able to define it as a surplus plasmon. Even the title of the paper was showed here on a remarkable case of uneven distribution of light in a diffraction grating spectrum. That means he was not at all able to understand whether it is a surplus plasmon or not, because at that time no one knows that there is the existence of surplus plasmon. Okay. So it was in 1968, Otto and Krushman excited surplus plasma of silver using the attenuated taut inner reflection couple, and which actually opened a new way for scientific community. So far we discussed the coupling of light and electron. So the next question is how we can confirm this coupling. So we know that resonance will happen only for a particular angle if the wavelength was fixed. So if we started to observe the reflected light by varying the theta, what will happen is all the light, we will get reflected light here like here, that is showed here, and when the resonance was happened, then all the light will be transformed into the surplus plasmon wave. So at that point, we will get a cut in the reflected light. And if we plot angle versus reflected light, the graph will be like this. And the angle at which the resonance happened is known as surplus plasmon resonance angle. And this angle is defined as sine inverse 1 by n1 root of n2 square nm square divided by n2 square plus nm square. Here n1, n2, nm are the refractive index of the prism, dielectric media and the metal film. So, and the other thing about surplus plasmons are they are generated at the metal dielectric interface. And why metal dielectric interface? Because it need an interface between a positive and negative permittivity. And we all know that metal possesses negative permittivity and air possesses the air being dielectric media possesses positive permittivity. And the permittivity of a material is its ability to get polarized when it is interacted by an electromagnetic wave. And it is a complex quantity, and its real part tell how much material get polarized when it is interacted by a light, and the imaginary part tell the loss encountered while polarizing the material. And for here, for a neutral atom, uh, we know that its center consists of positive atom and it is surrounded by a negative charge. But when it is interacted by an electromagnetic wave, the charge shifting will take place like this. So this we can call it as dipole, because here two equal and opposite charges are separated by a small distance. So we can call it as dipole. But if we consider a bunch of atoms like this, then this effect can be named as polarization, because polarization is defined as the electric dipole moment per unit volume. So interaction of photon with the electron resulted in the polarization of the material. So to understand the behavior of electron, we can actually consider Broad model. And according to this model, the free electrons are like a gas, and which can move anywhere they wanted. And equation of motion for electrons are given here. And solving this equation, we will get the permittivity. And this permittivity is a frequency dependent quantity. That means material possesses different permittivity value in different frequencies. And since we need negative permittivity for surplus plasmon resonance that we already discussed, we need some range of frequencies for a particular material. And equation shows that uh, permittivity will be negative only up to a particular frequency called a plasma frequency. And the plasma frequency, again, we can define plasma frequency like that. It is the frequency up to which a material exhibits plasmonic property. And this plasma frequency have direct dependence with the carrier density. So by tuning the carrier density, we can actually tune the plasma frequency of the material. And this figure shows the carrier density of some material and the plasma frequency range at which they are exhibiting. And since metal like aluminum, copper, gold have high carrier density in the range 10 raised to 22 per centimeter cube, its plasmonic property or its plasma frequency comes in the UV range. And for nitrides, silver, alkali metallides, its carrier concentration is 10 raised to 21, and thus its plasma frequency is in the range visible range. And for zinc oxide, tin oxide, indium oxide, its carrier density is in the range 10 to 20, so that they exhibit near IR plasmonics. And for germanium and silicates, its carrier density is in the range 10 raised to 19. Thus, they exhibiting IR plasmonics. So here also we can understand that while increasing the carrier density, plasma frequency was also increased. But as well as a metal is considered, its carrier density is almost constant, it's almost fixed, so that we cannot tune the plasma frequency of a metal. So that is the one of the disadvantages of metal while using as a plasmonic material. And also, this plasma frequency can act as the boundary between the reflection and transmission. So, as far as a material is considered, up to plasma frequency, all the frequency reflect, and after plasma frequency, all the frequency will transmit. So, this is the reason why metal transmit X-rays and reflect all other wavelengths. So, the exponential decay of surplus plasmon wave in dielectric and metal region was showed here. And the exponential decay of surplus plasmon wave in dielectric and plasmonic material is represented by delta D as well as delta Pm. And for the X component of the electric field, Since there is no boundary, it is conserved in the x direction. But unlike the x component of electric field unlike Ex, the z component is actually forced to change due to the different value of permittivity for metal as well as dielectric here. So this continuity makes polarization change in the interference, and hence it is very clear that why the S polarized light was not suitable to excite surface plasmons, because only P polarized light can do the same. And also the effect of surplus wave was more observed in the dielectric media compared with the metal media. So we can say like that SPR is very sensitive to the dielectric media. So any change in the refractive index of the dielectric media will affect the surplus plasma resonance, and this we can actually uh, find a shifting in the surplus plasma resonance, and actually this property can be used for the sensing purpose using these plasmonic materials. So the dispersion relation of light line evanescent wave and surplus plasmon wave are showed here, and one could realize from the figure that there is no point at which wave vector or momentum of light line and surplus plasmon polaritron meets. Okay, so there is no chance for coupling to take place because the behavior of light was linear, and so when the frequency increases, wavelength should decrease. Even if the behavior of evanescent wave was linear, for a particular frequency, it possesses a different momentum compared with the light line. So, if we consider surplus plasmon wave, its behavior is non-linear, and it can have maximum frequency called the surplus plasmon frequency, and which is related to plasma frequency as omega st equal to omega p by root 2. And we can also see that there is a point at which wave vector of plasmon and evanescent wave meets here, so that the wave vector can be considered as the coupling wave vector of the surplus plasmon with the light. So the momentum mismatches that we described earlier was once again proved using this dispersion relation. Now I think we can consider some interesting things of nanophotonics. So while moving to the history, this cup is known as Lycurgus cup. It is a luxury item used by Romans around 300 AD, and this glass consists of silver as well as gold nanoparticle. And the peculiarity of this cup was when light illuminates, it shows different color inside as well as outside. So the reason is when we are looking the surface, we are actually seeing the reflected light, which is green color, and by placing source inside and looking from outside, we actually seeing the transmitted light, and which was in red color. And there are some interesting stories that people tried to explain this. Uh, it was in 1958 onwards, the British Museum started to preserve this cup. And for quantitative spectroscopic analysis, they actually sent their sample to a research lab. And these researchers traced the presence of gold and silver on glass. And they confirmed, and they actually reached in a conclusion that metal combination may result in color pigmentation, and that may be the reason for this color. But it was in 1962, this sample was again sent to Dr. Robert Brill of Corning Museum of Glass. And this is the world's largest space dedicated to a display of contemporary art and design in glass. And what he explained is this formation of submicroscopic crystals or colloids of metals was the reason for this color. And again in 1980, that means after the discovery of electron microscope, this cup was again examined by Barber and Freestone using TEM and XRD, and they revealed the presence of gold and silver of diameter 10 to 100 nanometer. So the thing is, if the metal particle size are very small, then the band gap will increase. So it is very sensitive to the particle size. That means for a gold particle, if the particle size change from 1 to 10 nanometer, they transmit as well as reflect different color. And that may be the reason for the different color in this sticker also. So now we can consider some nanophotonics in nature. So we know that butterfly have beautiful color and it will not shade if we kept for long years. So it shows that color in the butterfly was not due to any color pigment present in the butterfly. And after the discovery of electron microscope, scientists took the magnified image of the butterfly and they wondered seeing the structure. So it actually consists of a periodic arrangement of nanostructures, and a single wing of butterfly actually contains different types of periodic structures, and the interactions of light with these nanostructures resulted in different color upon incidenting light on different angles. And the same effect can be seen in peacock feather also, and the same reason can be explained. And next, we are considering some applications of nanophotonics. So first, we are moving to nanophotonics in communication. So if we consider the history of communication, it starts from smoke signal to radio, telephone, fax, and then finally reach to the handheld devices. Modern communication system need to transport huge amount of data with the ever increasing speed. And figure shows that as time increases, the demand for high operational speed was also increased. But electronic devices cannot perform an operating speed greater than gigahertz. So photonic devices, even if at a high operational speeds are able, they cannot be miniaturized because of the diffraction limit. So here plasmonics are the only solution because they are actually the combination of electronics and photonics, so that plasmonic material can be miniaturized as well as when to go for the higher operational speed. So next we are considering some limitations of the present mode. So we all know that current communication system are based on either electronics or photonics, and these modern electronic devices for information processing and sensing are functioning almost close to their fundamental speed and bandwidth limitations, and which is a serious problem. And electronics, which deals with the flow of charges or the electrons, and but when the frequency of an electronic pulse increases, the electron device become hot and wire become very loose. So hence, by the principle of we can say that higher the frequency, higher will be the data transfer rate. But if you use higher frequency, then a huge amount of data can be transferred. But here, using electronic equivalents, if we increase the frequency, it will went to a serious problem. And if we again decrease the size of the electronic wire, its resistance increases, but the capacitor remains the. So this also resulted in the resistor capacitor delay of electronic equipment. So in fiber optic communication, light was used to carry the information, and optical fiber is used as a channel for between transmitter and then receiver end. And we all know that they transmit light along the axis by the process of total internal reflection, and it consists of a core surrounded by a cladding layer, and both of which are made up of dielectric material. And to confine the optical signal in the core, the refractive index of the core must be greater than that of the cladding, that we all know. And the lateral confinement size of the optical cable is approximately lambda by 2, half the wavelength of light used. That is one of the drawbacks of the optical fiber while using as a channel. So to combine high operational speed with the miniaturization, we cannot use electronic devices as well as photonic devices, because the size and performance of the photonic devices are constrained by the diffraction limit. Because if we decrease the size, what will happen is there will occur the interference between the closely spaced light wave, and thus the width of optical fiber should be at least half the wavelength used while propagating. So we need an alternative solution for this. So we need to think what is next. So plasmonics is a new technology which use surplus plasmons as a way of guiding light, and it can transmit signals at optical frequencies along metallic surfaces much smaller than the wavelength they carry. And the plasmonic structures can exert huge control over electromagnetic waves in nanoscale. So in plasma, the information is carried by surplus plasmon photonons instead of photons, because we already understood that photon can be coupled to the free excited electron and thus can make surplus plasmon. So the information carrying optical wave can be coupled to the surplus plasma, coupled to the free electron, and surplus plasma can be generated. And this thing can be sent to the receiver end without any long optical fiber. So this is how we can use the plasmonic properties in communications instead of optical fiber. And these surplus plasma polaritrons are the electromagnetic wave which is coupled to the charge density oscillation at the interference between material of negative permittivity and positive permittivity. And I already told you that in fifth generation we are actually using microprocessor, and in microprocessor we are using buses or data lines for data transfer from one part of the microprocessor to another part. And here also we can use the plasmonic property because the surplus plasma polaritron can travel along the nanowire which act as the interconnector to in order to carry information from one part of the microprocessor to another. And again, a chain of nanoparticles can also be used to transport this electromagnetic wave from one nanoparticle to another via the near field electrodynamic interaction between them. But the loss of the plasmonic materials are huge compared with the photonic loss. So this actually makes a hurdle to the development of plasmonic communication. So still researchers are going in this field. Researchers are going in this field to minimize the loss of plasmonic, and I think we can hope that one day we all will be equipped with the plasmonic based devices. Next, we are considering discussing the applications of plasmonics as a sensor. So there are many types of sensors available in the present market, and out of which gas sensor, I think gas sensor have more importance in the laboratory purpose because every day we are dealing with the different types of gases, and some of them are non-toxic too. So if you consider typical human nose, it consists of almost 400 types of scent receptors, and which enable us to smell about 1 trillion of different odors. And but still, many of us do not have the capacity to identify the type or the concentration of the gas present in our atmosphere, and this is where sensor comes in. So gas sensor is the one where we have to detect the variation in the concentration of toxic gases, and in order to maintain the system safe and avoid any unexpected threats. So there are various gas sensors to detect gas like oxygen, carbon dioxide, nitrogen, methane, ammonia, hydrogen, etc. And they can be commonly found in devices that are used to detect the leakage of the harmful gases, monitor the air quality in industries and offices, etc. So, the type of gas the sensor could detect depends on the sensing material present inside the sensor. And normally, these sensors are available as modules with the comparators as shown here. And these comparators can be set for a particular threshold value of gas concentration. And when the concentration of the gas exceeds this threshold value, then the digital pin goes high, and the analog pin can be used to measure the concentration of the gas. So this is how a standard gas sensor works, and its dimension was almost 3 centimeter by 3 centimeter. So based on the concentration of the gas, the sensor will produce a potential difference because it will change the resistance of the material inside the sensor. So which can be measured as output voltage. And based on this voltage, we can actually consider what type and concentration of the gas can be estimated. But the same sensor can be prepared using a plasmonic material with a dimension less than zero point 0.5 by zero point 0.5 because we already discussed about surplus plasmon resonance, and the surplus plasmon resonance at the metal dielectric interface was very sensitive to the refractive index of the dielectric material. So if air was mixed with the gas, then it will result in the shifting of surplus plasmon resonance, and this shifting is proportional to the concentration of gas. And same setup can be used for biosensing also because so that we need to functionalize the material in the surface of the plasmonic material, and we need to put the suitable antigen and take the SPR dip, and then again by adding the antibody again take the SPR dip, and thus sensing can be understood. So this plasmonic material can be used as a biosensor as well as a gas. So, so next we are considering the applications of nanophotonics as hyperlens and superlens for far field and near field super resolution image. And there are some class of materials which are human made, and thus we can call it as artificial. And for those, the properties were derived from their internal structure rather than the chemical composition, and they are called as meta materials. So meta indicates that characteristics of the material are beyond what we see in nature. And here I classified material into four categories depending upon the sign of permeability as well as refractive index. So the normal optical properties of the material comes in the first category. That means having positive permeability as well as positive refractive index. And for plasmonic behavior, we know that we need a negative permittivity. So plasmonic material comes in the blue region. So if material has both permittivity and permeability negative, then they are called metamaterials. And these material possess negative refractive index also. Mathematically, we can tell it as a positive refractive index, but for the time being, we are actually telling it as a negative refractive index. So metamaterials are the materials having both negative permeability, negative permittivity, as well as negative refractive index. And these materials are not at all naturally occurring materials. So we can now consider what are the applications of these metamaterials. And in the first figure, we can see three medium having positive refractive index. And we know that all non-natural material have positive refractive index, so that the light crosses from one medium to another gets slightly bent in the direction of propagation. And if the refractive index is more, then more will be the bending. And suppose if we replace the second medium as a negative refractive index slab having a small thickness, so then the light will be bent as opposite in normal bending, so that the light inside the material we are able to so what happens is we are able to focus the light inside the material. So what happened is this concept actually break the image of lens first coming in our mind. So that if you have refractive index material having small thickness and have negative permittivity as well as permeability, then we can convert it as a lens. So any paper like a material having this property can be converted as a lens. So this is the one of the advantages of metamaterials. So, the figure shows that image formation using a super lens made up of silver, and we can see the image nano here. So we already understood that how to focus the light using negative index materials. We can actually focus the light, but how we amplify them? So this we can done using a evanescent wave, but how? So. Any object is visible to us because it emits electromagnetic radiation. So if we consider an object plane and image plane, and the problem of imaging is concerned with the reproducing of electromagnetic field distribution in the image plane. Suppose the electromagnetic field emitted by an object can decompose into Fourier components kx, ky, and kz. So when moving from object plane, the amplitude changes and image became blurred. That we all know. Suppose z is the propagation direction and this Fourier component kz is a complex quantity. So the real kz represents the propagating wave and the imaginary kz represents the near field component of the non-propagating modes whose amplitude decays exponentially with the distance from the source. So normal conventional lens cannot see this imaginary kz, so that they are designed to correct the phase change only. So it is in the near field component carry the finest details of the object. So to restore their amplitude in the image plane requires some amplification, and which is of course beyond the power of the conventional lens, and hence the limitations to the resolution. So to get a perfect image, we need to satisfy two conditions. That means correcting the phase, and next one is amplify. And correcting the phase can be done using a metamaterial, and next one we need to amplify. So in such a super lens, the electromagnetic waves that reach the surface of a negative refracting index lens can excite a collective movement of surface waves known as electron oscillation known as surface plasma, and this process enhances and recovers the evanescent wave, and this is the near field imaging. So I hope you all understood about superlens, and next we are moving into the hyperlens, far field imaging using hyperlens. So now we know that light from the object consisting of two things, propagating as well as non-propagating things. And propagating wave have low wave vector, and this evanescent wave have high wave vector. And the first one carries large feature information, and the second one carries the fine details confined to the near field. And since evanescent wave cannot reach far field, it cannot contribute the final image in normal conventional lens. So the realization of hyperlens in far field super resolution imaging relies on two basic requirements. First one is a material that supports wave propagation with a high wave vector, and second one is a magnification mechanism that is conversion of high wave vector wave to low wave vector wave, so that the super resolution information can be sent to the far field. Considering the first one, after long research on metamaterials, researchers found that anisotropic plasmonic metamaterials provide one of the most practical options to fulfill the material requirement. So, the simplest anisotropic plasmonic material can be constructed by depositing alternative layers of metal as well as dielectric. So the name hyper, because it satisfies the hyperbolic dispersion relation, because here we consider it as a stacking of two different material having two different permittivity. Here in the x direction as well as y direction it is almost same, but in the z direction it is varying. So it actually obeys the hyperbolic dispersion relation, and thus it's called as hyperlens. And for the second one, can be obtained, magnification obtained, that means conversion of high wave vector to low wave vector can be obtained by bending the flat layers into concentrically curved layer. And this will result in the conservation of angular momentum, and thus the tangential wave vector are progressively compressed as the wave travel along the radial direction. And the magnified image carried a low wave vector will ultimately be formed at the outer boundary of the hyperlens before propagating to the far field, supported by the surrounding environment. So the development of superlens and hyperlens made it possible to get optical microscope without any diffraction limit. So we already discussed about this, because using the superlens and hyperlens we can actually construct a microscopy. And next thing is nanophotonic biosensor, and this also we already discussed, using plasmonic material as a biosensor. And I think we can conclude this discussion with this. So the conclusion is we have discussed the various possibilities of nanophotonics in various applications, and which gives some hope for advanced technology development in future. And thank you.
Okay, thank you, madam. It was a very nice talk.
Thank you.
And I have few queries just to understand,
Okay.
just for understanding purpose only. Actually, you have told for coupling the plasmonics or coupling the plasmonic waves, we need a momentum matching. So
Yeah.
if we take a two-dimensional or three-dimensional plasmonic material, we can use a prism grating or some periodic materials to match the momentum. But suppose if I am taking a nano material, let's assume it's a zero-dimensional material, whether we require a coupling agent or not.
No, actually, this plasmonic, surplus plasmon can be considered in zero dimensional, one dimensional, like that. So, what you is in 0 dimension, that means localized surface plasmon. So the main requirement for surface plasmon is a metal dielectric interface, and that can be obtained in LSPR also. So here momentum matching is not all a large criteria, because while illuminating light on a nanoparticle, we are not at all making any things to make this momentum match. In grating also, we are not at all making any methods for this momentum matching. Hello?
Yes. Okay.
Yeah.
So you are telling if it is a nanoparticle or sizes is far below some 10 nanometer or 20 nanometer, you can shine directly the light. It will, if it is a metallic nanoparticles, automatically the surface plasmon resonance will occur. Like that only you are telling.
Somehow the condition will be satisfied, but we do not. There is no need to give anything external for that. Somehow that will be
Okay.
satisfied.
Otherwise, it would be a problem for us because nano dimension means it's already very small. How to make a prism or something like that to couple? So it will be okay. Anyway, it's not necessary. So it's okay, fine. And one more thing, just I want to ask. Once you discussed about that liquor gas cup, after this TM analysis, they understood that it is coated with silver and gold nanoparticles. And said that its band gap is depending upon the particle size. Its band gap is varying. Whether these metals have really a band gap or not.
Yeah, actually, while making as a material in nano dimension, even the metal possesses the band gap, because we are actually know in quantum dots, this light, the illumination of light or the emission of light was depend upon the band gap of the material. So while considering it as a nanoparticle, band gap comes of even if it is metal.
Even though it's a metal, at nano regime, the metal may possess the band gap. That's what you're talking.
Yeah. Because even the gold changing the nano dimension from 1 to 10 nanometer, it's actually reflecting different color due to the variation in the band gap.
Okay. Question.
Hello.
Yes. Is it audible?
Yeah. You can continue. Yeah.
Okay. You said that you are negative refractive index, and with that we can get super lensing. Could you please suggest or give some examples for realistic examples for this negative interaction in negative refractive index materials? Or could you please give some realistic example for how we are using this negative refractive index materials for the super lensing?
Yeah, actually, I told you that for a negative refractive index, what the minimum criteria is, its permittivity as well as permeability should be negative, so that we can assume that its refractive index also will be negative. So we can actually find out the permittivity from permittivity value of a material from by extracting from Drude-Lorentz equations. So if we find out that for a material having negative permittivity, then we can consider it as a negative refractive material. Like if we stack, I already told you that while making hyperlens, we can actually stack two different material having positive and negative permittivity, and this will actually gives us negative refractive index. So if we consider like zinc oxide material and some doped zinc oxide material, for a particular frequency, doped zinc oxide material possesses negative permittivity, but but the undoped zinc oxide material may not have that property. So by stacking these two, we can actually get a negative refractive index material.
So you are telling.
It's actually metamaterials are not all naturally occurring material. It's an artificial material. So that we need to make that material by understanding its permittivity value in that particular frequency.
So you are telling the doped zinc oxide and undoped zinc oxide itself will make a negative and positive refractive index material. So that is an example. Is it so? Okay. Thank you. It was a very nice talk. Thank you. Session is open for the audience. Thank you.
We have some questions in the chat box.
There is one question in the chat box. What is the difference in features of photonic IC and electronic IC? Features of photonic IC and electronic IC?
Photonic IC and electronic IC. So integrated circuit, but what by telling integrated circuit, what we are meaning is we are actually making all the electric components into a single device. We are actually confining all the electronic components into a single device. So if you are able to go for all electronic components into like transistors, resistors in a minimum single device, then we can't call it as integrated electronic integrated circuits. And for photonics integrated circuits, I don't know what it is.
Okay, ma'am. Next question is, what is surface plasmon resonance? One participant has asked, what is
Yeah,
surface plasmon resonance?
yeah. I already told that. Um For, if you are considering the interaction of electron as well as photon, surplus plasmon will be generated only if there is coupling between this electron as well as photon happen. So surplus plasmon resonance is the condition at which this coupling happened, and thus we get the surplus plasmon wave at the result.
Next question is, ma'am, what is optical, can you say about optical computer technology? Optical computer.
Optical computer. Okay. So so far we are using electronic computer. So to go for optic computer, we need to use the property of plasmonics. That means we need to go for this optical signal should be confined into some electronic equipments, and then we need to use that. I already told the plasmonics is not an emergent field; it's an emerging. So researches are only going on. It's not at all end. So optical computer means we need to confine these optical signals in electronic circuits. Then it will be possible. So optical computer will come only after the emergent. This plasmonic will emerge in uh, in these computer devices. Hello.
Any more questions from the audience? The feedback link is posted in the chat box. All are requested to fill the feedback and submit it before the next session. Thank you, ma'am. Thank you, Soumya, ma'am. It was a wonderful session. Thank you for enlightening us, sharing your knowledge. We all enjoyed the session. Thank you all. We will join you at 1:15.
Thank you. Thank you.
Thank you all. Dear participants, we request you to fill the feedback form and join us at 1:15. At 2:30, we will have our valedictory session. Our joint director, Beena ma'am, will join with us. Till then, we'll take a break. Thank you.
താങ്കളുടെ പ്ലാൻ വാലിഡിറ്റി 3 ദിവസത്തിനകം കഴിയും. തടസ്സമില്ലാത്ത സേവനങ്ങൾ ആസ്വദിക്കുന്നതിനായി റീചാർജ് ചെയ്യുക. Your plan validity will expire within 3 days. Recharge to enjoy uninterrupted services. നമസ്കാരം. ഫ്രഷ് ഹോമിലേക്ക് സ്വാഗതം. 100% ഫ്രഷും കെമിക്കൽ രഹിതവുമായ മത്സ്യങ്ങൾ, ആന്റിബയോട്ടിക്കുകളില്ലാത്ത ഹലാൽ മാംസവിഭവങ്ങൾ, മറ്റ് പ്രകൃതിദത്ത ഫ്രഷ് ഉൽപ്പന്നങ്ങളും നിങ്ങളിലേക്ക് എത്തിക്കുന്ന ഇന്ത്യയിലെ നമ്പർ 1 ഓൺലൈൻ സ്റ്റോർ. നമസ്കാരം. ഫസ്റ്റ് ഹോമിലേക്ക് സ്വാഗതം. എങ്ങനെയാണ് താങ്കളെ സഹായിക്കേണ്ടത്?
ഹലോ, ഞങ്ങൾക്ക് വീട്ടിലേക്ക് സാധനങ്ങൾ എത്തിക്കാൻ പറ്റുമോ?
അതല്ല മാം, ഞാൻ തീർച്ചയായും മാമിനെ സഹായിക്കുന്നതായിരിക്കും. മാം ആദ്യമായിട്ടായിരുന്നു ഫസ്റ്റ് ഹോമിലേക്ക് വിളിക്കുന്നത്?
അതെ, ഫസ്റ്റ് കോളാണ്.
അതല്ലേ, അവരുടെ പിൻകോഡ് ഒന്ന് പറയാം. മാം ഡെലിവറി ചെയ്യാനായിട്ടായിരുന്നു.
673611.
എവിടെയാണ് സ്ഥലം? എവിടെയാണ്?
കുരുവട്ടൂര്, കക്കോടി വഴി പാലത്ത്, കുരുവട്ടൂർ.
പിൻകോഡ് 6736.
Welcome back to the third session of our 3-day FDP program. There is no end to education. It is not that you read a book, pass an examination, and finish with graduation. The whole of life, from the moment you are born to the moment you die, is a process of learning. It's a great pleasure for me to introduce our speaker, Dr. Yusuf Karuwat, Senior Scientist of CSIR NIST, Thiruvananthapuram, Kerala. He has received his doctorate from CSIR NIST, Thiruvananthapuram. He is a recipient of Marie Curie Postdoctoral Fellowship. We are truly honored by your presence. I joyfully hand over the session to Professor Dr. Yusuf Karuwat to share his ideas on miniaturized spectroscopic devices for analytical purpose. Over to you, sir. Dr. Yusuf Karuwat.
Sir, okay, sir, it's audible. You can continue. Okay. You can share your screen and you can continue. Thank you.
So this presentation is visible. Hello.
Sir, hello. Sir, I think it's not audible properly. Yes. 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 Yes.
Okay. Yeah. So let me first thank Tina for her kind words of and I also would like to thank.
Sir, excuse me.
Yeah.
It's not audible properly. Can you keep that microphone very near to you?
Hello. Okay, come on.
Hello. Okay, sir. Okay, now it's okay.
Okay. Yeah. So yeah, let me first thank Tina for nice words of introduction, and I would also would like to thank Dr. Shivadasan for giving me an opportunity to speak with the teachers. Let us go to the topic. For today's topic, I have selected miniaturized spectroscopic devices which can be used for analytical purposes. I will not go into much details of different techniques. I will focus mainly on two of the techniques. So let us start. As you know, spectroscopy is the study of interaction between any materials and the electromagnetic radiation. As you know, it is what in spectroscopy, what we are exactly studying is the extent of interaction, that is either in terms of intensity or energy, as a function of wavelength or frequency or energy of the radiation. That is, we will have, if you have a spectrum of light, we will study the interaction of what kind of interaction is there at each wavelength. It can be represented in terms of wave number, or it can be represented in terms of energy, like that. So if you look into the electromagnetic radiation, we have a full range of electromagnetic radiation, and in each of these electromagnetic radiation can be used for specific application. For example, in the radio frequency range, that is VHF range, is that frequency range that we usually do in NMR analysis. UHF is used for EPR analysis. In the microwave region, it is actually what we are probing is the rotational transition of materials. In the infrared region, we probe the vibrations of materials. And the visible and ultraviolet region,
That is the normal solar region. What we look is the electronic transitions, whether they are going from ground state to the excited state, like that. And X-rays proves the ionization, and gamma rays proves the nuclear effect. So each of these can be used to figure out some aspect of material. So the spectroscopy, you might be familiar with the this story of the lost camel, right? So there was the story begins like this. There was a poor man who was having a camel, and one day he lost the camel, and he was searching for it, and he could not find the camel anywhere nearby. So he came when he was searching, he came across another person coming in the opposite direction, and he asked to that stranger, "Hey, did you find my camel?" So the man told, "No, I didn't see your camel." Oh, oh, wait. Let me ask you one thing. Whether your camel is blind in one eye? Yes. My camel is does not is not able to see on one side. So I think your camel might have gone through uh, this way. Maybe you can search this. So he moved along, and then he came across another person, second person, and he asked the same question to the second person also. "Hello, friend, did you see my camel?" So that man also told, "No, I didn't see any camel in this way. But let me know whether your camel is having lame in one leg." So the man replied, "Yes, it has a problem with one of his legs." "But you told you didn't see the camel, but how do you know it?" "Okay, you can go straight and probably you will be able to see it." Then the next person, he moved along and still he didn't see. And he came across the third person, and he asked the third person whether, "Did you see my camel?" He also didn't see the camel, but he asked whether the camel has a short tail. So how does these people who are not ever seen this camel say that these characteristic of this camel? So this is one ordering question, and you can see that uh, if the camel is blind on one eye, so the first person's answer is because he's on the way he found that there were no leaves on one side of the trees, and the second part there was a lot of leaves. So when the camel passes, he can see only one side, and he ate the leaves from that. So that is the reason why he didn't. Uh, uh, he uh, he assumed that it could be that camel. Similarly, the second person was observing the ground, and he could see that some difference in the footprint. So from that, he could assume that the camel is having lame in one leg. It is like that. So in the case of spectroscopy, you may not be able to 100% surely look into no say that this is the material, or no spectroscopic device will give you 100% answer to that identity. But you can see certain features in material which will be characteristic that one, and by combining all these observations, you may be able to arrive at one conclusion. That is the basic principle of spectroscopy. So for today's content, what I have selected is two topics. The first one is based on Raman spectroscopy. That is, in the first part, I will give you an introduction about Raman spectroscopy, and then I will try to explain you how can you design a low cost and portable Raman spectrometer that can be suitable for your application. Maybe you can fabricate it for your college, and you can teach your students with that one, and you can also do some experiments with that one. And I will also give you some examples on how this Raman spectrometer can be used for certain kind of applications that is required in the society. In the second part, I will show you how we can use a smartphone. Smartphone is something that is available with all of us. So how this smartphone can be used for a spectroscopy. So in this one, I will give you an example how we can use smartphone as a spectrometer for sensing of certain metal ions. So the basic logic of today's talk is to enable all of you, or at least some of you, to develop cost-effective analytical devices for your own scientific research and application, as well as for demonstration to students for their practical sessions. Or if you do some research work in your lab, you can see how you can develop your own devices. So let us go into the first topic, that is Raman spectroscopy. Raman spectroscopy, as you all know, it was works based on one of the important discoveries made by Sir C.V. Raman in 1928, that is Raman effect, and for which he was awarded Nobel Prize in the year 1930. So after that, every 28th February, we are celebrating this day as National Science Day. So what is actually probing in Raman spectroscopy? Probably some of the previous speakers might have explained to you. As I told you, it is the interaction of electromagnetic radiation with the material. So when a light interacts with a material, there are several things that can happen. The first thing is that it just passes through the material like you pass the light through a glass window. So nothing happens, it passes, except that there can be the phenomenon of refraction, that is bending of the light. The second one is that, like, you look into the mirror, there are reflections is possible. There also material does not interact anything much with the incoming radiation. And then in the case of absorption, certain frequencies of light will be absorbed by material, or in some instances, the material will absorb the light and re-emit in a different wavelength. So that is called as the fluorescence. The other thing is the scattering. Okay, the material when the light hit on the surface of materials, it can scatter into different directions. So the Raman spectroscopy, so this is also the origin of different Jablonski diagram. That is what we usually teach in our colleges, which gives you some idea about the origin of different spectroscopic techniques. So in any material, you are having different energy states. Energy states corresponds to rotational levels, vibrational levels, electronic energy states. So in each electronic energy state, it is will be having different vibrational and rotational energy levels. So in the case of IR, what we are probing is the transition between two adjacent, or between two vibrational levels in the same electronic energy level. That is what you measure actually in the case of IR spectroscopy. Whereas in the case of UV visible spectroscopy, what we are usually probing is the transition of electrons from the ground electronic energy level to the lowest excited state. And in the case of fluorescence, what we are probing is the return of electrons from the excited state to the ground state. And similar to that one, if there are some kind of phenomena like intersystems crossing, that is usually the fluorescence occurs from singlet excited state, while the phosphorescence occurs from the triplet excited state. So when you look into the Raman spectroscopy, as I said to you, it is actually probes the vibration of a material, and you can see that the IR also probes the uh, vibration of the materials. So in the case of Raman spectroscopy, the molecules will be interacting with the material and will be going into a virtually excited state. It will not go into the electronically excited state, but it will go to a virtually excited state, and from there it instantaneously come back to the different vibrational level. So if it is the incoming radiation is having a wavelength higher, or the energy is less than the incident radiation, then we call it as a Stokes Raman scattering. Or if the incident radiation is sorry, the outcoming radiation is having an energy higher than the incident radiation, then we call it as an anti-Stokes scattering. So if you look at this Rayleigh scattering is that there is no energy difference. Okay, so it goes to the virtually excited state and then comes back to the normal, the original vibrational state itself. So if you look into the IR, you can see that it is the transition between the different vibrational levels. Whereas in the case of Raman, it involves an virtually excited state. But if you take the difference between the incoming radiation frequency and the outcoming radiation frequency, you can see that the difference will be corresponds to the difference in the energy of the different vibrational levels. That is, it will be almost equivalent to the IR spectroscopy. That means it is probably the vibrational levels of the materials. The most important thing is that, as you know, that any vibrational spectroscopic technique is a characteristic for a material, and it is can serve as a fingerprint information about that material. So if you consider from the see, if you have any doubts in between, you can ask, or at the end of also it is fine. So if you consider device from the device point of view, you can see that the IR is an absorption-based device spectroscopy. That is, if you consider the instrumentation, it will be having an IR light source and IR detector, and the sample will be kept in between, and the detector and the IR light source is in a straight line. They are kept in a straight line. So what you actually monitor is the intensity of the incoming radiation and the intensity of the outcoming radiation. Whereas in the case of Raman spectroscopy, what we are Raman scattering, the beauty is that the scattering is a three-dimensional phenomenon. Okay, when you hit the material in one direction, the scattering can be in any of the three-dimensional directions. So you can keep your detector anywhere with respect to your excitation and light source. That gives you a large flexibility of instrumentation, and you can develop different types of instruments for Raman spectroscopy applications. So why Raman spectroscopy is one of the most important technique for today's these nowadays analytical purpose is because of certain advantages features it is having. As I told you, it works based on the principle of scattering, so that you can have high design flexibility for instrumental fabrication, and it uses you can use any monochromatic light source. Whereas in the case of IR spectroscopy, you need to have a IR light source. But for Raman spectroscopy, any monochromatic light, whether it is UV or it's visible, green, red, or even IR light sources can be used for the Raman spectroscopy measurement. And it is actually a non-destructive technique. Usually, for any spectroscopic measurement, you need to have preparation of samples. For example, IR measurements, you will be mixing it with KBR powder and making it into a pellet. So after that measurement, you will not be able to reuse your material. Whereas in the case of Raman spectroscopy, the main advantage is that you don't require any sample preparation method. can directly use any materials as such, even living organisms. You can probe in measure the diamond spectroscopy of the living organs without killing them. So that is the beauty of the method, the technique. That is, it is a non-destructive technique, and similar to IR, it is gives you the fingerprint information. So because of that one, it will be highly specific. And nowadays, the diamond measurements can be completed in few seconds. So it is a rapid, sensitive, and cost-effective analysis. As a result, it is used for different on-site and point of care applications. Like it has been used in the analysis of food items for contaminants, toxic materials, like that. Pharmaceuticals for quality checking, as this is one of the serious analytical area. Most of the time, the pharmaceuticals are many of the times you may not know that the pharmaceuticals are fraudulent materials. So if you want to have a quality control, you can use diamond spectroscopy. It is used in the identifications of chemicals in the laboratory as well as in factories for checking for their raw materials as well as quality control of their products. And the narcotic people can easily identify the narcotic materials and can take proper actions immediately. Otherwise, most of these analysis, you need to send the samples to specific laboratories, and it would require a longer period of analysis. And it is also being used in the detection of explosives, and one of the emerging area is the imaging and diagnostic area. So as I said you, it is suitable for a wide variety of on-site applications, and it is also a valuable tool for analyzing meshes. I will give you an example of that one. Minimum then there is the most important thing is it has minimum interference from water. Usually IR, if you take it, if you have some water content in that one, you will not be able to make the measurement. For one thing, that is the spectrum will be overwhelmed by the diamond IR spectrum of the water. The second thing is that the KBR will be is hygroscopic, and it is will dissolve be in the water. But in the case of diamond, you will not have much interference. Usually the peak comes around 3000 centimeter inverse, and it is a very, very weak in intensity. So it will not normally interfere with any of your measurements. As a result, it is suitable for biological systems, even in living conditions, and it is highly sensitive. Nowadays, there are new techniques like surface enhanced diamond spectroscopy methods, where you use nanoparticles and you can improve the sensitivity like anything to picogram, ppm, ppb levels. So these are some of the importance of Raman spectroscopy. There were several challenges in the field. One is actually the extreme dose scattering cross section. That is usually it is around 1 in 10 raised to 6 photons are inelastically scattered, and there are also interference from highly intense ray-like scattering. So if you give around 100 photons into a system, more than 99.999% will be the Rayleigh scattering, and you will have only 0.0001% diamond scattered photons. So what does it mean is that if you want to record the Raman spectrum, most of the time the detector will be saturated with Rayleigh scattering itself, and you will not be able to detect the Raman. These were some of the initial difficulties that were faced in Raman use of Raman spectroscopy for analytical purposes. So people were using high power lasers, extremely sensitive detectors, and usually I think I even during my PhD I remember that for recording one diamond spectrum, it took almost 1 day. One day, if you keep the sample in the morning, you will get the result only in the afternoon. But there were several advancements in the field, and nowadays you can have handled pocket size or mobile phone size diamond spectrum. And there were several developments actually that has caused from the bulky instruments to the handheld version. And the most important things I would say is the invention of lasers. And in the lasers itself, nowadays the most prominent one is laser diodes, which you can see in all our computers for CD reading and other applications, CD writing, and these. So they use laser diodes actually. So these laser diodes are also now. So your excitation source is very small in size, so you can reduce the size of the instrument a lot. And in the beginning, the detection was accompanied by the photographic plates, and later it was moved to photo multiplier tube. And nowadays, most of these diamond spectrometers uses the CCD, which was invented by Boyle and Smith in 1969. And so that, as I showed you in the last slide, the diamond spectrometers are reduced the size into even a pocket size version. So if you look into if you want to buy something from the market, these are some of the prices that you may have to provide. You can have high-end systems, that is diamond spectrometers coupled with microscope systems, and it costs more than 100 lakhs. And there are portable systems which cost up to 50 lakh, and there are handheld devices which cost around 30 lakhs. So let us see how to design. If for now, let us come to the our topic: how to design a low-cost Raman spectrometer for your own applications. So if you want to fabricate any spectrometer, you need to understand it is working principle as well as its device layout actually. So in the case, this is the given is the device layout for UV visible absorption spectrometer, where you are having D2 lamp and tungsten lamp as the light sources, and then you are having monochromators. Monochromators are actually used to split white light into single light. For example, white light, if you want to have a 532 nanometer alone, and then you can use monochromator, or by moving that monochromator. I will come back to that point later. So the monochromators will give you monochromatic radiation out of that one, and then you have a beam splitter, and one of the beam splitter splits the incoming radiation into two halves. One half will be passed to your sample, and it will be going into the photodiode. The second part will be going into your reference sample, and it will be going to the for another photodiode. And then you are having the data processing unit like your computer, and you will have the readout. This is in the screen. So in this one, the Beer it operates based on the Beer-Lambert's law, A is equal to epsilon CS, or log I0 by I. I0 is the incoming intensity, so you can get it from the reference sample, because it will not absorb any light, so that is I0, and I will be the light coming out of your sample. And if you look into the fluorimeter also, this is the device layout for the fluorimeter. Normally, fluorimeters are equipped with xenon arc lamp, which will give you highly intense and broad emission spectrum. And then you will have a monochromator for selecting the wavelength, and then you will have a cuvette holder where you can keep your samples. And the emitter light is collected by optics, and then it is passed through a monochromator to split the wavelength the emission light into different components, and is analyzed with a detector. Normally it's a photodiode detector or a CCD detector. So the important components of any spectrometer devices is: one is the light source, then you have monochromators for analyzing the spectrum, and then you are having a set of focusing optics where you can clearly focus the light into the sample as well as into the detector, and then you are having control electronics to control the switching on the lamp, moving of the monochromator, the collection of photons at the detector, and then you have data processing at the computer. Now, if you look at the Raman spectrometers are also available in different configurations. As I told you, it is a very versatile instrument, so you can have different configurations. So the first one is actually a 90-degree configuration, which is almost equivalent to our fluorimeter, where you have the light source and your detector kept at 90 degrees with respect to the sample. So the excitation comes like this, the emitter light goes like this. So that in this case, the Raman scattered light will be coming here and it will be fed into the detector. And the other option is the back scattering or 180-degree option, where your incoming light source and diamond scattered photons are collected in the same direction, backwards actually. So this is actually a 90 backscattering configuration. We will go more deep into this one, and then you are having like our absorption transmission based Raman spectrometer, where on one side you have light source and the other side you are having the detector. And there are new instruments like spatially offset Raman scattering instruments, where your light source and the diamond scattered light are separated by a distance. So you will be radiating on one side and collecting the diamond scattered photons from the other side. So this is actually the spatially offset diamond scattering. And then what you are having is actually the most advanced is the tip enhanced diamond spectroscopy, where you use probably in the morning you had a session on that one. So you use an AFM tip to localize the electromagnetic radiation, which gives you enhancement in the polarizability. So you get a large enhancement in the diamond scattering. And there are also wide angle illumination and other methods. Probably you can go to this review and find out more information on that. So now let us go to the first category, that is the backscattered configuration. That is the one we are going to demonstrate here. So this is actually, if you look in the device point of view, this is the actual device layout for the backscattered Raman spectrometer, where you are having a source that is usually a laser source, and then you may be having specific optical filters, where these optical filters allows the passage of only one wavelength, this one, because the light source may emit another wavelength as well. So the spectrum will be complicated. So to minimize that one, you usually use a laser line filter, and then you are having a beam splitter like you saw in the absorption spectrometer. There is a beam splitter, and the light coming from the source is directed. This beam splitter will be actually oriented around 45 degrees with respect to your excitation source. So this will allow you to turn the light around 90 degrees with respect to the incoming radius. Okay, so the light comes from here and goes to the lens, and the lens actually focuses the light into the sample. And the Raman scattered light will be collected back by the same microscope lens or the objective lens or the normal convex lens, and it passes through the beam splitter. And the beam splitter, half of the light will be going to this source, and half of the scattered light will be going into the detector part. Okay. So any Raman scattered, Rayleigh scattered light, if it is going to the detector, it is going to saturate the detector, and you will not be able to see this Raman scattering efficiently. So in order to remove this Rayleigh scattering, normally you need to use a notch filter. Notch filter means it blocks one radiation and passes the rest of the thing. Or you also use a long pass filter. Long pass filter means if you have a 550 nanometer long pass filter, everything below 550 nanometer will be blocked, and above 550 nanometer will be passed into the detector. Detector actually, we will come back to this one later. This consists of a CCD detector and a grating and then plate. So we will go into different components wise. Let us see the first component. So if you want to make a Raman, make a fabrication of a Raman spectrometer, the first important thing that you have to choose is a light source. As I said, lasers are good for good laser for as an excitation source. So there are important parameters that are going to affect your measurement of the qualities of the excitation source that are going to affect your measurement are the first one is the wavelength of the excitation source and the monochromaticity of the light excitation source and the wavelength stability, wavelength stability and the optical power of your excitation source. Okay. Wavelength actually influences your measurement because the Raman scattering efficiency, the efficiency of Raman scattering actually varies inversely with respect to lambda raised fourth power of the wavelength. That is, I is proportional to lambda raised 1 by lambda raised to 4. That is, if you are going to increase the wavelength, your Raman scattering efficiency will be drastically decreasing. Which means that if you use a UV light, you will get a better Raman scattering. If you are going to use a IR light, you will have a low efficient Raman scattering. Then, as I said, you the Raman shift is actually measured as the delta difference in the frequency, that is delta mu 1 by lambda 1 minus 1 by lambda 2, where lambda 1 is the wavelength of the incoming radiation, and that is excitation source, and lambda 2 is the wavelength of the scattered photon. So if your light is having more than one wavelength, you can see that each of these wavelengths will contribute to Raman scattering, and your spectra will be more complicated. So you will not be able to clearly figure out the exact material. So that for that reason, you need to have a highly monochromatic light. And also the next important parameter is the wavelength stability. Wavelength stability is important because if there is a change with respect to time, if there is a change in the lambda 1, you can see that the Raman shift is also going to shift, right? So there will be a shift in the observed Raman spectra if the wavelength is not stable. And the most important part is power, how much power you require actually to see this Raman transit. So if you want to make your own Raman spectrometer, you need to choose a laser. So you can see that in the market, or if you Google in the eBay or Amazon, you can find different types of laser pointers. Probably in our classrooms, we use laser pointers, which is having a power of around 5 milliwatts. There are also laser pointers which is having power up to 100 milliwatts, which is actually used for decorative purposes. So you can choose this kind of laser sources, and if you try to see what is the wavelength of this, the one we demonstrated here is actually a 532 man, that is a green laser diode, which was having a power around 70 milliwatts, and it is having a wavelength around 532 nanometers, and it has a monochromaticity or line width of emission is around 1 nanometer. And with this one, if you calculate, you can have a spectral resolution of 35 centimeters in good. So if you unscrew all these this one laser diode, you can see that it contains a lot of components. Actually, it has a collimating lens, that is the incoming light has to be collimated. It has to move in a straight line, and then you are having a aluminum housing, which is useful for dissipating the heat generated while laser is working. And then there is an electronics board, that is driver board for supplying the power. And the second part is the probe optics. Probe optics, as I told you, it contains a beam splitter and an objective lens and a splitter. So in this case, the functions of this probe optics are to maximize the collection efficiency of the weakly scattered diamond radiation and block the Rayleigh scattering radiation entering into the detector unit. So beam splitters, actually there are different types of beam splitters actually available in the market, which split the light 50 to 50 or 30 to 70 or 60 to 40. Like that, whatever ratio you want, you can have it. And there are actually some dielectric or silver coated glass substrate actually. Okay. And they are a little bit costly. But if you want to have a cost-effective solution, what you can have is that you can use a normal microscopic slide, which you use in biological labs and all. You can cut that one into a square piece, or even you can use a cover glass also. That is around 2.5 centimeters to 2.5 centimeters. And if you keep these glass light around 45 degrees with respect to the incoming light, you can see that one part will be passed through that one, the rest of the one will be reflected. So if you use, what we found is that this the transmission and reflection ratio is around 70. That is 70%. If you keep a glass light with respect to the incoming light, it passes around 70%, transmits around 70%, and 30% will be reflected. So if you have a 70 milliwatt power, will have around 40 milliwatt is transmitted and around 20 milliwatt will be reflected. And for focusing lens, you can use the normal convex lenses that is available in your laboratory, which does not, or you can buy from a local market. Or nowadays, this also comes with 3D print, plastic printer actually. So it does not cost much plastic material. Or there are, if you look into the YouTube, you can see how you can, even from your drinking can, how you can make a convex lens. Okay. So we used a convex lens for this instead of microscopic objective lens. And then we used a long pass filter around 550 nanometers. So the laser light and Rayleigh scattering will be below 550 nanometers, that's 532 nanometers. So it will be blocked, and the diamond scattering actually occurs about 100 to 200 nanometers above the excitation light. So all the diamond scattered light will be passed through the laser, long pass filter, colored or glass filters, and you can block the. Now coming to the detectors are actually in the times I told you, it is uh, uh, photodiodes, photo multiple tubes are used. Nowadays, people use it is CCD. CCD has multiple elements, and the CCD is very cheaply available. It costs around 1,000 rupees, and you can see this kind of CCDs in our normal instruments like scanners. It is present in our mobile phone. It is present in these barcode readers. So these CCDs are widely available, and it can be can get for a price less than 1,000 rupees. That is the sensor part that we have used it. So the spectrometer actually is a device. It is an instrument used to measure the properties of light as a function of electromagnetic wavelength. Or typically, it is used in identification of materials. And there are also small USB devices which you can hold in your hand, like from Ocean Optics. Ocean Optics costs around 4.5 lakhs. And there are science surplus also, and we have this one is from Kochi, this Hallmark, which costs around 2 lakhs or something like that. And Research India is another Indian company, which is also cost around 2 lakhs rupees. Okay. So if you want to make a spectrometer by your own, you can have different components. You need to understand what are the different components in that one. Normally, you are having an entrance slit. Entrance slit is micrometer size opening. It is having as a size around 50 or 100 or 25 micrometers. And then you are having the light coming out of this one. This slit will be going in a divergent fashion. So you will need to collimate that one. For that one, you will be using a collimator. And then you are having a grating, or instead of grating, you can also use uh, prism, so that light will be split into its different components. And then you are having focusing mirror or lenses, which can focus the light into your CCD detector. So these are some of the important parameters that you can choose. You need to be understood how these properties of these materials, these components actually influence the spectral resolution of your instrument. Actually, if you use a 1800 lines per mm grating and use focusing lenses 50 centimeter, 5 centimeter and 5 centimeter, and chip size of around 50 micrometer, you will get a resolution of around 0.52. And if you are 0.2 nanometer, if you are going to use the same parameter and change the little bit to around 25 micrometer, your resolution will be better, around uh, 0.3 nanometer. You will be able to get it. And if you are going to keep the slit size same, and you are going to keep the focal length of this focusing lenses the same, and if you are going to reduce the number of lines of your grating, the chosen one is having 1200, and the rest of the parameters are constant, then you are going to have a resolution of around 0.8. So you can understand that these parameters are important in deciding the resolution of your spectrometer. So the main components, the CCD I already mentioned, it is the linear CCD, Toshiba 1304, which is you can see in barcode scanners or our normal printer scanners, or even your mobile phones also. And this is how, okay, I will not explain this one. This is actually how the spectrometer is actually working based on monochromator. Don't worry about this one. And this is one illustration where how does the system actually influences the size and resolution of your instrument. Actually, if you have a 0.5 nanometer resolution, you can see that the spectra are clearly distinguishable. Right, you have different peaks. But if you are going to reduce the resolution to 10 nanometer, all the peaks will be merged into a single peak. So in the case of Raman, this is much more important because what you are going to see is highly narrow peaks. So the resolution is something that is much important in this one. So in so based on this, as I told you, if you based on this one, you can actually do a 3D printing of your case and also arrange these components. Here is an example of what I have seen is a 3D printed box actually for our spectrometer, and this is actually the entrance list, and this is a 5 centimeter focus lens, and then you are having this is another 5 centimeter lens, and we are going to hold our CCD in here. Okay, this is CCD 1304 CG CCD, and you which is about DG that is going to, and this is actually the diffraction grating. So you can, based on these dimensions that you are having from the previous slide, you can actually have a design of the position of these components, and then appropriately you can have a 3D design of your case, and then you can actually print it. It does not cost much of this one. And to work with CCD, you can either use a Arduino controller board microcontroller, or you can use STM32 microcontroller. Okay, and this can be connected to your computers via USB. Okay, so or it can be even connected to your mobile phone if you know some little bit of knowledge about the app development. This can be even connected to your smartphones actually. So this is one of the spectrometers actually we fabricated in our lab through 3D printing. And to fabricate this Raman spectrometer, as I told you, this is so we saw what is the probe optics. We also saw what is the laser source and what is the detector. So what you can do is this is actually the actual device configuration tested in a optical table actually. So this is your laser source, 532 laser source, and this is the glass normal glass plate. You can see that light hits on this one, and then it will focus into your sample. This is here is the lens actually. So this is focused into your sample, and the diamond scatter lights are collected here back, and then you are having a long pass filter here, and it is connected to your detector via fiber optic cable. Okay, and you can easily collect the diamond spectra here. Once you have this idea, you can take, you can have either a 3D, make a design the components for, the case for the entire optics actually, which is an example. And we have implemented this one in an old instrument box, which is having a size of around 25 centimeters, 15 centimeters, and around 10 centimeters. Okay, so this is our laser source, which we have taken out from this laser pointer, and then you are having this beam splitter or the microscopic slide, and this is the lens, and this is actually the portion of the long pass filter, and this is the focusing lens, and this is the detector, and it is connected to your one. And this can be either, as I told you, it can be either 3D printed, or even you can decide with this what is this polymer what is it polymer box actually, not PLA. Anyway, this is polymer sheet actually, which is very possible. All together, together you can have it in the piece can be fabricated in. If you are using polymer sheet, you can fabricate it in 1,000 rupees. If you are going to do the 3D printing, you can spend it in 10,000 rupees or something like that. So this is now coming to the application of this Raman spectrometer. So now you have seen how to make a Raman spectrometer, and now coming to the application side, actually I will little bit more. I will show one example here, that is quantitative estimation of methanol from ethanol mixture. Okay, ethanol is actually mixed with methanol, and you can see that this is the Raman spectrum collected in our fabricated devices, and you can see that methanol and ethanol are very closely resembling chemicals. They are different in only in the number of carbon atoms and hydrogen atoms. But even that difference, you can see that it is clearly visible in your Raman spectrum. So whether if you have a library of the Raman spectra of your methanol and ethanol, you can just compare this one with your library, and you can see that whether it is a methanol or ethanol. That is how this identification actually works. And the other important parameter is actually quantification, how to quantify these components in this mixture actually. And you may be aware that UV visible absorption spectroscopy and IR absorption spectroscopy are actually absolute technique. That is, if you are going to change any instrumental parameter or measurement conditions, your absorbance is not going to change. It will be the same unless otherwise you increase the concentration, right? So if you are going to increase the stick size, or you are going to increase the indication time, the absorbance will be almost the same in this one. Whereas in the fluorescence and diamond are two different techniques, which are arbitrary measurement actually. So when you plot the intensity, you are either measure it as counts or arbitrary units. Okay. So the problem with that one is that if you are going to increase the intensity of your laser, the, then your diamond intensity also going to change. If you are going to increase the collection time, that is integration time, then also diamond intensity changes. Likely like that, if you change any measurement parameters, the diamond and fluorescence intensities are going to change. So it cannot be this is an example methanol and ethanol. So what to develop an algorithm, what we have done is we try to simulate the mixtures having different concentrations. So these are the Raman spectra of the mixtures of varying compositions. And you can see that the peak at around 880 centimeters, if you are going to increase the concentration of methanol, the peak at 880 centimeters is going to decrease, which is coming from actually the ethanol part. And if you are going to increase the concentration of methanol, you can see that ethanol, you can see that the peak at 288.16 is going to decrease. Okay, so you can see that certain peaks will be going up in certain peaks will be going down in. So if you are going to plot the variation of the intensity with respect to the concentration of the component, you will normally get a straight line. Y1 is equal to M1 plus X, M1X plus P1, Y2 is equal to M2X plus P2 for these two intensities actually. So if you are going to increase the laser intensity, this is going to change. This intensity is going to change and things won't work. So when you can do a mathematical operation of this equation, actually y1 by y2, you can do it, and finally what you can arrive at is a concentration factor x is equal to r1 divided by y1 divided by y2 minus r2, where r1 is equal to c1 by m2 and r2 is equal to m1 by m2. So now if you are going to say, measure these, so there is only one variable that is going to influence your measurement parameter is the ratio of the obtained intensity. The concentration is inversely proportional to the ratio of the measured intensity actually. So what you can see that you can see the concentration, if you are going to make the measurement of different radiation power 100 to 5 milliwatt, you can see M1, C1, everything is going to change, right? 100 is minus 64, M1 and 12 is minus 14, like that. But you can see that these R1 and R2 are constant, right? It does not have any influence on the radiation laser power. So this is irrespectively is constant. So that means that using this equation, by measuring the two intensities, you will be able to predict the concentration of the methanol. And for based on that one, we actually wrote an algorithm right from the switching on the device and to data acquisition, and there are little bit data processing involved in it. I will not go into detail. And finally, the device will be able to display the concentration of this one. This is, and the whole process will be over in less than 5 seconds. So in 5 seconds, you will be able to predict the concentration. Similarly, we also have applied this one for detection of edible oil adulteration. Edible oil adulteration is another important problem that is faced by our society. Every day in the newspaper, and most of the days in the newspaper, you see that coconut oil is adulterated with cheaper oil. Okay. So for this one also, I will not, in the interest of lack of time, I will not go into these things. Probably I will go and show you, yeah, this is actually the identification of adulterations in medicine, and I will directly go to the smartphone-based analytical devices. Smartphone is something that is easily available in our all our hands. Whether we will be able to use this smartphone for certain analytical applications. There are several reports nowadays coming in the literature. You can see that this is used in different applications, including the measurement of detection of viruses. Now, this is an example of in 2019 where they were able to detect even a few numbers of viruses in the sample. So nowadays people are also looking to use these mobile phones for detection, or we are also trying to develop some mobile phone detection system for coronavirus. That is something we are taking care now, investigating now. So the smartphone base, you know that the smartphone is one of our favorite thing, and we cannot nowadays we cannot live without that one. We can without that one, right? We use every day, every time, every second of our life. We use smartphone. So it is actually it is like an organ of our organ itself. And I don't think we will be in the near future we will be able to avoid this device actually. The smartphone is important. I don't know how many of you know that most of our smartphone have artificial intelligence facilities incorporated into that one. Certain applications work based on artificial intelligence. And the other important thing is that the price is not that much high. You can buy the smartphone from around 4,000 rupees to even lakhs of rupees. And most of even the cheapest ones will have most of the features which are present in the costly devices. And if you look into the smartphone, you can see that it is actually contains a lot of sensors actually. Right from your display camera, there are it is equipped with rear camera, front camera, dual camera, quadruple camera. The camera resolution is 54 MB, something like that. You can see that, and it has vibrators in that one. It has also has GPS sensors, Wi-Fi antenna, vibration sensors. A lot of sensors are present in our smartphone, and whether you'll be able to use. So this is a device that actually we can use for many of our analytical applications. So this is something you can look into it actually. And what we have used is demonstrated this one is actually sensing of two toxic metal ions from water, that is lead and mercury from aqueous body. You can see that, and for that one actually what we use is the metal nanoparticles as one of the components. And the metal nanoparticles has the advantages of easy to prepare. You can easily prepare these samples, and they exhibit. Most important is that they exhibit brilliant color. Even low concentration of nanoparticles will have bright color. Gold nanoparticles will have a wine red color. Silver nanoparticles will have a yellow color. So they are actually excellent candidates for colorimetric sensors. And this is an example how that they change their color with respect to the concentration of the toxic metal. And you can see that if you are going to add mercury to the nanoparticle solution, this is a silver nanoparticle solution. If you are going to add silver nanoparticle solution into the if you are going to add mercury to silver nanoparticle solution, you can see that the color fades down and finally becomes transparent, completely transparent. And if you are going to probe the absorption spectrometer spectrometric measurement, you can see that the intensity of the plasma absorption of silver nanoparticles is around 400 nanometers. It will be coming down, 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 down with respect to the concentration. So this means so it is the color is actually different. Similarly, if you are going to interact silver nanoparticles with lead ion, you can see that the color actually changes from yellow to red. And if you are going to see this absorption, you can see that color changes mainly because the absorption, the silver nanoparticle absorption at 400 nanometers decrease with the emergence of a new band around 500 nanometers. So that is why the color is actually changing to red. So yeah, and we also tested this one within different concentrations of metal, but we could see that only these two metals are sensitive to silver nanoparticles. And there are two independent mechanisms. One was actually plasma coupling, the other one was mercury oxide with amalgamation. So I told you this absorption spectrometers are measured with absorption spectrometer, and you can see that this absorption spectrometer, the components are actually light source and dispersion device, that is either grating or and you are having a one plate, and then you have a sample and a detector, right? So whether our smartphone will be able to use or can be used for this application without any absorption spectrometer, that is something we actually looked into it, and you can see that the smartphone is equipped with a camera, right? Rear or front cameras, several cameras are available. So you can use that one for photographing of yourself or others or even super nanoparticles. Anything you can photograph with that one, right? So if you look into the how does the camera works is that it contains a CCD sensor in that one. A 2D is an array of sensors, and each sensor is sensitive to it will this CCD is also have a thin layer of a color filter actually. So it will have red, green, and blue color filters in this CCD sensor. Okay, so this is something that creates later, but it has three different color filters. So it senses the color based on the intensity of the light. So if the light falls on the on each pixel, and each pixel is sensitive to a different color. So if the light is falling on the red pixel, and it passes only the red light into the sensor and CCD sensor, and it will give you an current with respect to that one. If it is passing through the green filter, only green will be passing, the rest will be. So by measuring these intensities of these sensors, you will be able to identify, compute the color. That is how it actually works. So if you look into the digital cameras, it has the red filter is actually, it passes in the range 600 to 700 nanometers. Green filter actually passes in the range 500 to 600 nanometers, and the blue filter actually passes in the 400 to 500 nanometers. There is one more sensor that is present in our cameras, that is IR filter. So it removes of all the IR light going into the detector. That is that I have not mentioned here, but there is IR filter. As well, for certain applications, you can use that one as well. But and let's say several the other important parameter is the how to characterize color is HSV. HSV is a linear color code actually. The color is represented in an angular fashion. That is, H is the angular representation of the color. You can see that how the color is varying. This is actually from one color to the other is varying H value, and the saturation actually is an intensity measurement. How intense is each color? That is S value, and varies is we actually depends upon the lighting condition. How much intense light you are providing. So that is these are RGB and SSB are two important parameters that you can be acquired taken from any of the color photographs. Okay, whether your photographic normal camera or even from your mobile phone camera. So this is once you have this photograph, this is one software that is image software. It is open source software. You can easily find it in the internet, and you can use it freely. This is an open source software, and you can use this software for actually extracting the color values of the material, any photograph. So this is an example I have shown it. This is the RGB and variations of for these bottles with different Hg plus ion concentration, and this is actually for the impression software. This is done with the image J software. So now, if you try to analyze how does these parameters are going to change with respect to mercury or lead ion concentration, you can see, you know that the mercury actually causes decrease in the intensity of this 400 nanometer, 400 to 500 nanometer, right? So, and there is nothing happening above 500 to above 500 nanometers. So you can clearly see that only the blue component, B value of your photograph is that what is going to change. Whereas if you look in the case of lead, you can see that in the case of lead, you are having a decrease in the intensity of the blue component, and an increase in the intensity of the what you see is the variation of all the R. I mean, red is about 600 nanometers, so it's green component actually. So altogether, you see variations in the blue and green value, right? So now, if you are going to plot intensity blue component with respect to the mercury concentration, you can see that it actually varies in a linear fashion. Similarly, if you are going to plot G component R plus G component, which is coming to representing the new band formation, you can see that in the case of lead, it is linearly decreasing. So this is actually the linearity actually tells you that this can be used for quantitative measurement. Similarly, in one case, it is you can see that it is fading of the color. Right. So the saturation value in the case of mercury, it is actually the fading of the color. So what you can actually see is the decrease in the saturation value. Right. Whereas in the case of lead, you are having a change of color from yellow to red. So your H value is that one changing linearly with respect. So either R or RGB values or HSV values can be used for quantitative purposes. And if you have a little knowledge on the Android development platform, this is there is some software available, freely available. One is Android Studio development software. With that one, actually, you can develop an Android application. Okay. So we had this algorithm. So this will take this algorithm actually take your photograph of your silver nanoparticle, and you can select the region of interest of your photo and estimate RGB, HSV values of this one. And what it is say that if the H is between 55 to 65, it is same RGB. That is this is say if it is a silver nanoparticle solution. And similarly, unknown sample, you can take it and select the region of interest and estimate RGB values and HSV values from the region of interest. And you can compare the reference as well as this unknown sample. And you can see that if your R is equal to approximately a reference and G is approximately G reference, G is greater than G reference, then it is mercury is present. If it is no, you can look for R, how RGB values are, and if this condition R is less than RF, G is less than GRF, G is greater than GRF, then it is mercury is present. And based on this calibration curve, you can actually do the quantification as well. So this is an example how this mobile application software with simple photography, you will be able to measure the constant. This is comparison between mobile application image-based software and the high-end absorption spectrometric device. All of them are matches with each other. So this is a small video regarding this Android platform, whatever you can develop.
So is there any technical issue?
Yeah, you are not able to hear?
I think you are not audible, sir.
Is that audible now?
Yes. Yes, sir.
Yeah, are you able to see the video?
Yes, yes, sir. It is 2:30 now. We have to stick on the time. So, hope it is clear now. You can continue.
Okay, that is all for today. And what I want to conclude is that Raman spectroscopy is a powerful tool for material identification, and you will be able to develop your own Raman spectrometer if you want to do it. I hope if you want have any doubt, you can either write to me or you can contact me by phone. Or similarly, by using a smartphone, you can use for different spectrophotometric applications. And I would like to thank my students as well as my collaborators who have actively contributed to some of these developments. And finally, I would like to thank you.
Thank you, Dr. Yusuf Karawat. Your thoughts have enlightened our minds and have shown us a new path. Thank you so much. Any questions from the audience? Okay. On behalf of GPTC Perinthalmanna, my gratitude to you for gracing the occasion and sharing your knowledge. Thank you, sir. Thank you.
Okay, welcome.
Thank you, sir. So, dear participants, personal details and overall feedback will be provided during the validatory session. All participants are requested to fill the feedback form without any mistakes. It will be taken for certificate generation. So carefully fill the feedback form. Certificates will be distributed within 2 weeks through email. We will not be entertaining any changes in the name or other details in the certificate. So please ensure that you have filled the feedback form correctly. Thank you for your cooperation. Now, we are moving towards the validatory session. It's the biggest day in the history of GPTC Perinthalmanna. We have hosted an online FDP. Welcome to the validatory session of Faculty Development Program GPTC Perinthalmanna in collaboration with SITR on miniaturized machines and devices. I invite Mr. Jamshed from Department of Electronics to deliver welcome speech.
Am I audible? Okay, this very happy that we are now in the validatory function of this FDP, and my duty to welcome all the participants, all the members are assembled here, and here we are very blessed with the presence of Binapi, JD in charge of RDTE, has joyfully accepted our invitation, and she is with us now. And I extend a very warm welcome to Beena Madam. And next I welcome our principal in charge, Mr. Pradeep Yam, who is always motivated and infuse us with energy for this program. And I welcome you, sir. And next I welcome Mr. Shivadasan, who is the coordinator of this FDP. He planned and executed this FDP very well. And I welcome our coordinator, Dr. Shivadasan, Assistant Professor of Physics. And next I welcome Mr. Pragashan P, HOS of Electronics Department. And I welcome you, sir. And next I welcome all the participants who are with us through this WebEx platform for last 3 days. And also I welcome all the staff members and the organizing committee for this function. Thank you, everyone.
Thank you, Jamshed sir. I joyfully hand over the session to Dr. Shivadas for course briefing.
Thank you. And today we are going to the end of the session, which is miniaturized machines and devices. sponsored by State Institute for Technical Teachers Training and Research, SITTER, Kalamassery, and hosted by Government Polytechnic College, Perinthalmanna, Malappuram. So just I want to brief the complete sessions, 3 days complete sessions in a quick way. Just first I have entered a session on light matter interactions in nanomaterials. So in that sessions we have discussed about how light is interacting to nanomaterials in subdiffraction regime, and there we have demonstrated some few realistic examples of some nanomaterials which size is far below the diffraction limit. And second section we have Dr. Keshavan Dhanasekaran from IIT Palakkad, and who dealt with additive manufacturing. In that sessions we have learned how we can do a metallic 3D printing with the assistance of high temperature using laser beam ablations. It was a wonderful session, and we could be able to understand how different types of small metallic devices which we are making. And next sessions with Dr. Subrata Ghosh. Dr. Subrata Ghosh from University of Manchester, UK. He explained us what is a supercapacitor and how its energy is stored, and how we can improve the efficiency of supercapacitor, and what are the importance of supercapacitor in our day-to-day life. It was wonderful. It was also a wonderful session. Next day, second day, first session was about Internet of Things, Instruments and Machines. In that section, Dr. Hamza Anjamikal delivered a nice talks on IoT as well as artificial intelligence, and he demonstrated so many small equipments by hand, electronic equipments with his hands, and he explained what are the purpose of each and every parts of the electronics instruments. And next session by Dr. Ansel V. About role of power electronics in miniaturization of power controllers and drives. And in that session, he explained how a power controller or how power electronics is helped us to reduce the power dissipations, and he demonstrated how an SMPS is helpful for us to save energy, save power, electrical power. So it was also an informative session, and we learned about how power electronics is working in miniaturization of electronic equipments. Next, Dr. Sanub Kumar from GPTC Nedungandam, he explained massive MIMO technologies for 5G and beyond 5G system. In that session, he could manage to explain how to improve the spectral efficiency of 5G for the systems, how to reduce the signal to noise ratio by adopting different channeling techniques. And that was a very informative session in the current aspects of science. Third day, first sessions was led by Dr. Sandana Kumar Parida with nanospectroscopy using tip-enhanced Raman spectroscopy, and he explained how we can correlate the spectroscopic techniques into atomic force microscopic technique, and he could manage to develop the incorporation of high resolution spectroscopic analysis, and he incorporated this spectroscopic technique to nanoscale regime. And next sessions from Center for Materials for Electronic Technology, CMET Athani, by Saumya K. She have informed, she have taught us the application of nanophotonics in miniaturized devices, and she could manage to explain how photonics is merged with plasmonics, and she demonstrated how these plasmonic materials can be incorporated for sensor applications. That was also a most modern topic in scientific industry. And the final last session by Dr. Yusuf Karwat from CSIR NIST Thiruvananthapuram, and she could able to manage the topic miniaturized spectroscopic devices for analytic purpose. And in that session, we learned how we can construct or develop a small spectrometer, including Raman spectrometer, and he could manage to develop his own spectroscopic instrument with a low cost. That is highly appreciated. And he could manage to explain us how he developed that small spectroscopic devices. It was a very informative techniques in for our country, because our economic criteria is very poor. In that situation, if we are making this kind of instrument, it will be very helpful for our country. Within these 3 days, we have learned so many scientific aspects from different areas, and it's truly beneficial for all of us. And I am very thankful for each and every resource persons. Once again, thank you from Government Polytechnic, Malappuram, Perinthalmanna, as well as the complete team of MMD 2020. Thank you. Thank you all.
Thank you, Dr. Shivdas. Now the session is open for audience. We are very happy to hear from you. We request our participants to give feedback of the program. You can unmute your audio and speak.
Hi, good afternoon. Myself, Dr. Devadas KM, Assistant Professor, Srivyasa NSS College, Vadakkancheri. We all are aware of technical as well as practical problems.
We are eager to hear from you.
Hello, can you hear me?
Yes.
Hello,
Yes.
Okay. Actually, yeah, we all are aware of technical as well as practical problems to conduct such a FDP in an online platform. It's really there are a lot of there will be a lot of problems and troubles, but the team were able to manage it very well. Well organized and a well planned FDP with eminent personalities. All the talks were of high standards and informative. It was a really great effort. I'm really happy to congratulate the whole team, for realizing such a FDP with eminent personalities in their fields. I extend my sincere thanks to SITTR and Principal of Government Polytechnic, Perinthalmanna, Sri Pradeep Sir, Coordinator Dr. K. Shivadase, and all the other members. Thank you. Great effort.
Thank you, sir. Thank you so much.
Good afternoon. Hope I'm audible.
Very good afternoon.
Okay. Myself,
Yes, you are audible. Very good afternoon. You can continue.
Okay. I'm Usha K, Assistant Professor, Department of Physics, EK Nayanar Memorial Government College, Ellerithattu. And my opinion about the program is it's a wonderful program, and learned lots of things within these 3 days. All the talks were effective and informative, and the program was nice and effective. And I think this types of programs really helps us to get some new ideas about the new research trends, and it will also help us to give some guidance to our students for their research activities. So I thank all the organizers and the team behind this FTP, that is Government Polytechnic College, Perinthalmanna for this wonderful effort. Thank you very much.
Thank you, Usha ma'am. Is there anyone to give feedback? Okay, thank you, dear participants. I request Mr. Pradeep, Principal in charge, to deliver presidential address.
Respected Dina ma'am, JD RDT Kozhikode, thank you for coming, ma'am. My dear colleagues and participants, I'm very happy and I realized that we can also do such a FDP program for the staff across Kerala in Polytechnic colleges through online platform. The material of each session will be available in our website and is in the YouTube. So I am very happy about the time management done by our resource persons and also our organizing team. I congratulate to all the team members. We are on the way of NBA accreditation and planning to go for next year to submit our SAR. And I know there is a lot of work behind that one and need a lot of things to do. But I assure that if we can be achieved by maintaining team spirit, and all our staff members are very keen to set up such activities throughout the next year. And we request all the support from JD RDT, JD Sitter, and our department for the progress of our institution. And once again, I thank to Dina ma'am for coming. Thank you, ma'am.
Thank you, sir. Thank you for your support and guidance. I'm delighted to welcome Ms. Veena Ma'am, Joint Director, to address the valedictory session.
Am I audible?
Ma'am? Yes.
Okay, thank you. Good afternoon. My dear Pradeep, the president of this function, and my dear colleagues. Now it's very happy to be with you for this validatory function organized by GPTC Perinthalmanna. First of all, I congratulate the team for organizing such an event, and I'm very happy to know that our faculties from I saw one name from Nedungandam as the resource person of one of the session. It's very proud. It's really a proud moment. That is our faculty becoming a resource person for this, for such a FDP. I congratulate the organizers for finding out such gems from our department itself. Because now our world is shrinking down to our hand. And the relevance of this type of programs are very much. That is miniaturized machines and devices. Even I am not at all aware of this type of devices, except this mobile. We were all dealing with very big, very large machines, very large computers. Even computers were very large when we were in colleges. Now we can take a computer and move around. Before it was not possible. It's a world of what shall I call, miniature devices. And this faculty development program is a need of the hour. And our institutions were able to organize such FDPs That is, we understood we could realize our ability to organize such programs during this pandemic, COVID pandemic. At least the COVID made us aware of our abilities. Before also, SITA was sending circulars, organize some FTPs for your faculties, but most of our polytechnics didn't accept that challenge. Now, during this pandemic, however, most of the institutes accepted the challenge, and we are organizing faculty development programs. Why not make this as a routine in our regular college hours? When the situations come back to normal, all the polytechnics can organize at least one FDP during a semester. And we can get rid of the load from the SITA, and SITA can think of more innovative ideas, implementing innovative ideas in the polytechnic community. So I hope more from GPTC Polytechnic, and with this team, I think you can do it. You can design your own FTPs and you can have at least one during a semester. And to the participants, teachers or teaching cannot be unlinked with learning. Learning is always part of our teaching. Teacher is always a learner, we say like that. And there is a quote by an American author. An illiterate of this century is not those who cannot read or write, but it is those who cannot learn, unlearn, and relearn. So we should know how to, we learn so many things during our post studies, during our teaching, everything. But new things, for adapting to the new things, we have to unlearn what we have already learned. And we have to learn so many things, like these miniature devices. We may not be able to adapt to those concepts itself. So we have to unlearn whatever we have already learned, and we have to relearn many things and teach our students also these things, how they can adapt to these changing world of technology. So a teacher is successful when he can make our students learn by themselves or adapt to changes. Now there is another term. Recently I have read about this. I don't know, sometimes you might have heard about this, but recently only I came across this word, RQ, resilient coefficient. Initially we were familiar with IQ, later then EQ came. Now I don't know when it is when that term came into this field, that RQ, resilient coefficient. That is when there is a struggle or something, all of us should be able to resilient back. We have to fight against this and we have to reach our goal. A teacher should be able to make our students adapt to these changes and be successful in their life. Then only our responsibility will be fulfilled. So I hope all the participants and all the teachers rise to such an occasion, such a standard, and make our students, we know our students come from various social background. We cannot expect them to behave like normal engineering college students or high school students and such. Their behavior is very, very different. There will be strikes, everything will be there. But in between that, we should be able to give a hand to our students and we should make them capable to fight against the changing world or find their place in that changing world. I hope all the teachers will be able to do help your students rise to the rise to a living standard which they dream. So once again, I congratulate the team for organizing such a function and inviting me for this program. Thank you, Pradeep. And I expect more FTPs for the faculties as well as for the students also. You can conduct the programs. We are planning one, and last time the Thrissur Women's College conducted one. Normally we used to conduct project exhibitions. Now it's not possible. So we can have our own way of conducting things for the students also. They are also expecting that from us. I expect more from the Polytechnic and wish you all success in your all endeavors. And I hope next year you can get the accreditation also. I wish all success to the team, GPTC Perinthalmanna, and the leader, Shri Pradeep. Thank you.
Thank you, ma'am. Thank you for your support and guidance. Now I request Mr. Prakashan, HOS of Electronics, to kindly propose felicitation.
Respected Joint Director, Dean Teacher, and our beloved Principal, Pradeep Sir, and the Program Coordinator, Dr. A.K. Shivadasan, and all other teams. I am also included in this team. Officially, behalf of this program, I will felicitate my words. First of all, I express my gratitude to Mr. A.K. Shivadasan. He take the challenge for conducting FDP program, miniaturized machines and devices in our college as part of the program. He arranged 9 eminent personalities, including our Shivadasan. Also, one Mr. Sanup Kumar from Nedungandam Polytechnic also engaged the classes very interestingly. On behalf of this program, I officially felicitate that the program is very interesting and valuable. I hope the team Perinthalmanna will also conduct another different programs in our institution very successfully. I hope. Thank you very much.
Thank you, sir. Thank you. Now, I would like to invite Shiva M.H. from department to conclude the session proposing Shiva M.H.
Respected Bina Ma'am, JD in charge RT Calicut, Mr. Pradeep, Principal in charge, guest speakers of FDP and participants from various institutions. First of all, I would like to express my gratitude to SITA for providing us all the and guidance to this FDP. On behalf of GPTC Perinthalmanna, I thank all the officials of SITA for giving us a platform through WebEx. I extend my thanks to Ramesh Sir, JD, for inaugurating our FDP. Your generosity and kindness towards our program has been overwhelming. I would like to thank Bina Ma'am, JD, for addressing the valedictory section. We request you to continue your support and guidance in our future endeavors. We are grateful to Ajita Ma'am, Project Officer, Sitter, for her guidance and support. I would like to extend my vote of thanks to all distinguished speakers who have accepted our invitation and broadened our vision. Thank you, dear speakers, for your wonderful session. On behalf of JPTC, I express my heartfelt thanks to all resource persons. A big thank you to our principal in charge, Mr. Pradeep, for his effort towards FTP. You have been a constant support and you have given us a lot of encouragement. I would like to thank the organizing team, teachers and supporting staff members of JPTC. Special thanks to our program coordinator, Dr. A.K. Shivdasan, and the program committee, technical crews headed by Mr. Sudhir Ketty, Mr. Atiq Rahman, Danish Moon, and Deepak. And I extend my thanks to all participants who have joined with us. Last but not the least, I thank Sina Ma'am, Associate Professor in English, who have anchored all this program. Thank you all.
Thank you, ma'am.
Mute ആണ് madam. Bina madam. Mute.
Thank you.
Okay, ma'am.
Dear
Okay.
participants, we request you to fill your personal details and overall feedback form without delay. Please make sure that your name and designation are correctly filled in the form. Ensure that you have filled the feedback after the session correctly. WB Eats said once, education is not filling of a pot, but the lighting of a fire. Education enhances our intellect and ability to make rational decisions. We now accept the fact that learning is a lifelong process of keeping abreast of change. With this thought, we conclude the FTP. Thank you all. Stay safe, stay blessed.
Thank you. Thank you.
Thank you all for your kind cooperation.